In this video, I'm going to explain how to build an interpreter, debugger, and front-end visualizer from scratch using TypeScript and React. I'll also provide a GitHub link in the description below. To get started, let's run this program, which just counts to 10. Down below, you can see the output. So let's run this again, but this time I'm going to put some breakpoints. We will add breakpoint support. So click run, and on the right side, you see the call stack. This is the global frame, which just contains the count variable after we've incremented it to 1. And run this a couple of times, and you can see on the right side that the count is going up, and here's the output. I'm going to remove this breakpoint. I'm also going to clear the output and then hit run, and that's going to run the rest of the iterations. Hit this one more time, and the program is now done executing. So I'm going to do another example, this time with functions. I'm going to write a function that computes the nth Fibonacci number. Okay, here's our function that computes the nth Fibonacci number, and this program is going to compute the third one. So I'm going to set some breakpoints so that we can see like how the call stack is propagating or is mutating rather throughout the entire program's execution. I'm going to run this. And you can also click on these frames to see where the program is paused. So for the n equals 3 instance, still waiting on left to be computed. Same is true for n equals 2, and this one we're about to return 1. After we return 1, then let's just continue. We're going to compute the 0th Fibonacci number, but if I click here, we're now paused over here, waiting to compute right. Whereas for the n equals 3 instance, we're waiting to compute the left still. So just run this a couple times, and you get to see how the stack is propagating. I'm also going to clear the output. I should have cleared this earlier because that was for the previous program. But I'm just going to keep running this, and eventually we will get to this point after we've computed the third Fibonacci number. Run one more time, and we've printed it. Our program is done executing. All right, so that's what we're going to build. Along the way, I'll explain the concepts, intuitions, and also my thought process. So without further ado, let's get started. This project will be broken down into 2 phases. In the first phase, we're going to build the interpreter and the debugger purely in TypeScript. And then the second phase, we'll take the debugger outputs and render it on the browser in React. So in front of me, I have this obligatory Hello World program. And if you're using Node 24, you actually don't have to compile this down into JavaScript. You can run the TypeScript as is. And let me just demonstrate that. Node main.ts. Here's the Hello World. Now, all Node does is it just strips the types. It doesn't do anything else, so no like full compilation or anything. Now, this unfortunately does mean that some language features will not be available, such as like enums or like parameter properties for classes. But that's not going to be a problem because we won't be using any of those features. All right, so step number 1 is we're going to make a tokenizer, which just breaks down source code into a sequence of tokens. So let's make the spec folder to contain our language specification and tokens file. So for example, if our if we had this piece of code right here, then the tokenizer is going to break this down into the count token, the equal sign, the 0, the semicolon, print, open parentheses, count, close parentheses, and the semicolon again. So now let's specify all the tokens that our language is going to support. So that there's 5 token types. There's going to be keywords, there's going to be identifiers, there's going to be strings, numbers, and symbols. So the keywords that we'll have, we're not going to have that many keywords. It's just if, else, while, true, false, null, fn, and return. And then an identifier is a sequence of alphanumeric characters that have to start with a letter. Oops, letter. Put in here. So for example, like this count would be an identifier, the print would be an identifier, and these are used to like just denote names, like variable names, or later on, like we are going to support objects, so that would also denote like keys. But this is just a sequence of alphanumeric characters starting with a letter. Now note that in many languages, you can have more like character types. Like in pretty much every language, for example, you can use the underscore in a variable name. We're going to keep things simple, and we're not going to allow that. Now, strings, a string is just a sequence of characters enclosed in the double quotes. So, like for example, like foo or like bar, or if I change up this program right here, let's say this let's just say for the sake of argument, this count is going to be a foo, and our tokenizer is going to produce a string over here. So those are strings, and then the number is just we're going to support both integers and also decimals. So it's a digit sequence, and optionally followed by a dot and another digital. Oh, I keep saying digital. Digit sequence. So this would be like an integer. This is just a sequence of digits, but it's not followed by this, so it's not a decimal number. Whereas this would be like a decimal number. So those are numbers, and then we have symbols. So symbols would be like the equal signs, the semicolons, like generally anything that doesn't fall into like these four categories would be considered a symbol. And these are all the symbols that we're going to support. So open parentheses, open bracket, square bracket, close square bracket, open curly, close curly bracket, the dot, the comma, and all of our operations, divide, modulo, this and, or, not, and I'm just gonna like type these out. But they should be like pretty familiar because these tokens pretty much, or these symbols pretty much exist in almost every language nowadays. All right, so these are our tokens, and now let's go ahead and create the tokenizer. Actually, I'm gonna create another folder called front end, and I can just call it FE, and then I'm gonna put the tokenizer in here because every interpreter can be roughly broken down into like two parts, which is the front end and also the back end. The front end is where we tokenize, and then we create something called an abstract syntax tree. I'll talk more about that. And then the back end is where we take the abstract syntax tree and then we just run the program. Our tokenizer is going to be a class that receives the program string as an input in the constructor. So let's go ahead and make a constructor. And also, let's put these tokens into types. So every token we have to also track. Actually, let's just make the tokens first. Keyword and type. Keyword type. The type is just going to be these. Then we have an identifier. Type is just going to be identifier, and we need to val space token. Actually, let's add the token suffix just to be clear what these types are. This is going to be string, and I think we're just gonna let the operator here. In case you're wondering, the autocomplete there is Gemini code assist. Yeah. Here's number. symbol, type symbol type, and copy all these symbols. Put it up here. I think I'm just going to get the AI to generate list, and let's just review it just to make sure that it's exhaustive. Okay. All right, double equals. We have all of our relational operators, equality, and the semicolon. Okay, so that's good. Type, symbol type, and I think I'm also going to introduce I'm also going to introduce an end of file token, which is not quite like in our spec here, but it does make it will make the next part, which is parsing, a little bit easier. It's EOF token type EOF, and all of our tokens is just going to be tokens are just going to be these, right? So another thing is that for each token we also need to include its location in the source code. So we need line numbers, we need column numbers, and we also need the index that appears in the source code. So I'm going to make this position interface. Just have line column, and I is just the one-dimensional index. And then we have the location as a start, and have the base token, which just has the I think we'll just have the location and each of these. Base token. All right, now we have all of our token types. Now it's time to implement the tokenizer logic. So the way that this is going to work is, let me just bring back our example program. Count is equal to 0, print count. We're going to look at, actually, let me bring back the token right side. We're going to look at the first character, and just from that, we can sort of tell which token type might start here. Because we know that by looking at this, it's a letter, so it can't be a string. There can't be a string that starts there, rather, and there can't be a number that starts there. There can't be a symbol that starts there, so it has to be either a keyword or identifier, starting where this C is. So because it's a keyword or identifier, what we'll do is we're going to collect the maximum sequence of alphanumeric characters that follows the C. And so we're going to get the count, or we're going to collect count. And then we just compare, is it a keyword? It's not any of these, and therefore it must be an identifier. So we're going to tokenize this as an identifier. Throw that down below. And then we're going to repeat on the right side of the program string. If we encounter a space character, we just skip it. It's not part of any valid tokens. Same is true for new line characters. Now we have this equal sign. Because none of these start with an equal sign, we know that a symbol has to start here. Now there's two symbols that could possibly start there, and that's the single equal or the double equal. And to disambiguate this, we just look at the character afterwards. Let's see, it's a space, it's not equal. And so the single equal starts here. And then we just repeat on the right side, the space, skip it, and then repeat on the right side. And we see now it's a digit, and therefore a number has to start here. So we're just going to collect all the digits, and then we check if it's a decimal. If it's a decimal, we're going to collect the dot and then the next digit sequence. But in this case, it's just a 0. We tokenize 0. and then we repeat on the right side, and then we're just going to keep doing this until we run out of characters to process, at which point we would have tokenized the entire program. We're going to make the tokenizer method, or the tokenize method, I should say, and all this does is it'll just create the tokens list. There's going to be, I guess we need a pointer. We're going to do this iteratively, we're not going to do this recursively, so we do need a pointer to check the current position that we're in. And I'm just gonna like code up like a rough sketch of how this tokenize function is gonna work, and then we'll modify this a little bit. So it is going to be a loop. We're gonna check if it's in bounds, then we're gonna look at the current character, and then we check, okay, if the current character is let's say if it's a alphabet character. So we'll implement this in a little bit, but all this does is it just takes a single character as input and checks if it's an alphabet character. So if it's an alphabet character, then we're going to tokenize it. Sorry, not this dot tokens, just be token. And we'll call it identifier or keyword, or keyword or identifier. But we're gonna try to tokenize this as a identifier or as a keyword, and we'll implement this in a little bit as well. But what this function does is it'll just like consume all the alphanumeric characters and then put I to the right of the token. And of course, if it's a digit, then we're going to try to tokenize this as a number. If the is this quote, we're going to try to tokenize it as a string, and if it's a symbol. But actually, symbols are a bit interesting because there's actually two types of symbols. There's single and double. So we could have we could have like one function that's responsible for just figuring out like whether it's a one character symbol or two character symbol. But I think the way that I'm going to do this is I'm just going to check if C is if C is a two-char symbol, or rather if C and the next character forms a two-char symbol, and if it does, then we're going to tokenize as a two-character symbol. Otherwise, if the one-character symbol, then we just tokenize it as a one-character symbol. We also need a bunch of continues here. Now we have the white space characters. So C is equal to this, and we just skip it. If C is equal to backspace, then we just skip it as well. Now here's the problem with this approach of putting this I in the tokenizer class is that we also have to track the line and the column, and so we actually need like a line, and we always start with the first line and the first column, and it's not just a matter of like incrementing the line, the column anymore, or rather, it's not just a matter of incrementing the I anymore. We have to increment the column every time we increment the I, and then every time we encounter like this new line character, we have to increment the line and then reset the column back to 1. So that's a lot of complexity for a tokenizer class, or for just our tokenizer class. So I'm actually going to create a helper called the incrementer. And what this is going to do is it's actually going to have a position element. Position, which starts at the default position, which is just line 1, column 1, and the index is 0. Did I say column? I think we're just gonna, let's not do line, let's just do column. Okay, let's delete this as well. And this incrementer class is going to have 4 methods. It's going to have, inc, gonna have the inc method, and yeah, it's gonna increment the position by 1. It'll have the new line method, which is going to increment the line and then set the position back to 1. It's gonna have the pause method, which is returns the current position, and then it's also gonna have the I method, which just returns the current index. Now, we don't technically need this method because we already have this information in pause, but this does keep the code simpler because in many cases, we don't actually need the entire, or in many cases, we just need the index. So let's go ahead and actually remove this I, and then instead, let's get the incrementer class. So read only, I guess we'll just call it inc, and we don't I here. So but there's going to be a little bit of a factor. Inc I and also one thing to notice is that because we're using TypeScript, we never have to worry about this giving us a array out of bounds error. It'll just give us undefined, and undefined is not going to show up as the second character of any of these or symbols, I should say. All right, so this is just this.inc. Whoops, this.inc.inc. But then for the new line, we have to increment. I guess we can continue. For the new line, we can increment, and then we can also set a new line. Then we have one last case, which is we encounter a character that is not part of any token. I think I'm just gonna throw an error because to keep it simple, or to keep this interpreter simple, we're gonna be very light on the error handling. Now all that's left to do is to implement these methods. So we'll implement these helpers later. I think I might just get the AI to implement this for us because these are like pretty easy. Let's just this. For now, we'll just make them. We'll just keep them empty. Keyword identifier token. Identifier first. Next one is num for token. String token. And yeah, these two functions. So let's implement the identifier or keyword token first. So yep, need that. I guess we don't really need this loop, but we do need a loop of some sort. So while this dot program, this dot inc dot I, so while this is alphanumeric this time, alphanumeric, whoops, we're just going to increment, but before we increment, we're going to put whatever character that we're looking at in this loop into val. We're going to collect it into val. And then at the end, we check is it a keyword? And if it is a keyword, then we're just going to tokenize this as a keyword. So we have a type error here, but this is keyword is going to typecast this val into a keyword type. So type, or I shouldn't say typecast, it's going to type guard. Or I'm not quite sure what the term is, but you'll see what I mean. Val, have an identifier here. Why is there a squiggly? Oh, right, because we need the location. We'll come back to the location in a little. All right, so number character. So while this is a digit, we're just going to collect all the digits into val. And then I guess we can have this, but before we do this, we actually have to check if the program, after we collect all the digits, if the next character is a dot. And if it is a dot, then we have to tokenize this as a decimal number, which is kind of what this part does. So this part puts the dot into val, and then increments, and then we just collect all the digits into val again, so that it's a decimal number. Now string is we have to increment this dot inc first because we had to skip over this quote. And then we're just going to collect all of the characters until we get to another double quote, which will have terminated the string. And afterwards, we can simply inc. Actually, do we need to increment this? Yeah, we do have to increment this because we need to skip over the last double quotes. And that's our string function. Now for the 2-character symbol, this is just the first character is, I guess we'll call it C, and second character is D. I forgot to put the const here. And so the and this one I think we do have to cast this one to a symbol type. And then the 1-character symbol is just this. But actually we have to increment this. So inc dot inc. And there we have it. I guess we can add in the location. At this point, like there's two ways to proceed. We can either implement these helpers, or we can implement the location. I think I'm going to implement the location first, and that's just going to be quite simple because we already have. Actually, I should use the right side here. We already have this position element. So for the identifier or keyword, we just simply get the starting point as the current position. And then we get the ending point. Right here after we've collected all the tokens or all the characters into val. And then this block is just going to be start and end. Lock is just going to be start and end. Why is there a squiggly line? Property is missing. Okay, so it looks like there's already there's actually another type, which is this location right here. So I guess we can't call this location. We can just call this log. Actually, I think if I export this, does that work? If I export this, then okay. So if I export this, then it's not going to yeah, it's not going to use the default location type. And yeah. Okay, so that gives us the location for the identifier or the keyword. Let's do the location for num now, which is basically the same thing. Is that we collect the start, we get the start here, and then once we're done with like all this, we get the end, and we simply just add a location start end, and then for the string, we have the start, and then we have the end, and then we have the location. For the 2-character symbol, start, end, and location. And the 1-character symbol is just same thing, start, end. Block is start, comma, end. All right, there we go. So that's gonna give us the locations, and now we just have to implement all of these helper functions. I think I'm just gonna get the AI to do this for us. Yeah. Okay, here are the helpers. Is keyword, check if it's an alphabet, is digit, is alphanumeric, is 1-character symbol, is 2-character symbol. This is the typecast / typeguard that I was talking about. Yeah, so at this point, we have completed the logic for our tokenizer. We could actually run this through the AI, through Gemini, just to see like what it thinks. Is it correct? So I think I'm gonna go ahead and do that. This is a token spec for language, and you can just copy paste like all the stuff in. This is the tokenizer, correct? And while this is running, we can also test it on our end. So whatever the AI gives back, I tend to find that the AI is actually pretty good at evaluating like a relatively like small amount of code like this. But if it tells you it's correct, it doesn't mean it's actually correct. You do have to take what it has to say with a grain of salt. But let's test it while Gemini is evaluating our code. Count. Here's our program, and then here's our tokenizer, new tokenizer. Yeah, let's just log the tokens to see what we get. Tokenizer, or sorry, it should be node fe slash tokenizer.ts, and what do we get undefined? Oh, right, because in tokenize, we actually forgot to return the tokens, and we also forgot to whoops, that's in the loop. Forgot to return the tokens, and we also forgot to put we forgot to put this one right here. Forgot to put the end of file. Let's try this again. All right, I guess we don't really have to worry too much about the location right now, but let's just check that the types are correct. So here's the identifier. That's the count. That's the equal sign. And then we have a number. Value is 0. We have that. The semicolon. X is print. X is this. Open parentheses. Count. This, and that. Then I guess we could also check the location, or actually let's look at what Gemini has to say first. So okay, there's some critical bugs currently. Oh, right. Speaking of the devil, we were just about to check the location, but I guess it's not correct because we stored a reference. So yeah, we could return a copy of the object. Let's go ahead and return a copy of the object. Okay, and what's the second one? We have an infinite loop. When you process a 2-character symbol, you grab the characters, but you never actually advance the increment. All right, let's have a look at that. 2-character, right? We never actually increment this, but let's just test it to see if that's actually the case. It should be true. And there's our infinite loop. So let's go ahead and increment inc.inc, test this. All right, here's that, and here's the end of file. Very good. If tokenize returns nothing, yeah, this is the error that this was the first error that we saw, and now infinite loop on terminates strings. Right. Okay, so we have to check if this. We have to check this for strings. Where's my string function? Here's the string function. Go ahead and add this in. Yep. And run this through Gemini once more. Actually, what is this? Your code explicitly handles space and you however code often contains these characters. Actually, we're just not going to handle these. We're just going to assume that this won't have these like random characters, missing end of file token. Yeah, that was another problem. Extraneous. Well, however, this is not included in this. I guess I missed it. We do need this when we start supporting objects. So that's a really good catch. I'm just gonna run the fixed code through Gemini once again, and also the new symbol spec, or new token spec, I should say, which only includes this. Okay, so let's just test it with some more programs. You can also get the AI to generate programs for you to test this on, but I'm gonna make some for now. I'm gonna test like while true. I guess print foo, and then print bar. And let's see this. We'll check the location in a little bit. Let's just see if this program is tokenized correctly. So we have while true, or while this true, that's open curly, Identifier is a print. Yep. String foo, very good. Yep. Print. We're gonna print bar this time, and close parentheses. Yep, and then the end of file. Okay, very good. So that's this type mismatch. Throwing on terminated string. Okay, I think I'm just gonna ignore like these two, and let's fix the type mismatch. Type symbol type. This one I forgot to include. I forgot to include this. Okay, there we go. So we have the semicolon, or we have the colon here. Oh, at this point, I think I believe this tokenizer is correct. I'm just gonna test it on some more programs. Oh, actually, you know what? Let's check the location first. So we can't really see it here, but let's stringify it. Okay. And put in a JSON, move it to the side, and see like if it kind of looks correct. So line one, while has 5 characters, column it is 6, I is now 5, correct. This should start at right, we're skipping the white space, so this should start at 7. It's only 1 character, so it ends at 8, 6, 7. Yeah, so I'm just gonna check this and I'm gonna check this with a bunch of programs, probably get the AI generated. Yeah. Okay, I've tested this with some pretty large programs, and I'm convinced that it's correct. So let's move on to the next part, which is parsing. Parsing is the process of converting the list of tokens into a more structured representation of the program called an abstract syntax tree, or AST. If you've never seen one, here's the Typescript AST viewer. On the left is a program, and on the right, over here, is its AST. Let me collapse some of these nodes. So at the top level, there's the variable statement. If you click it, it shows you which piece of code corresponds to it. So it's just this. And then there's the while statement, which corresponds to this while loop. If I expand the variable statement, there's the declaration list, and then there's the declaration. As part of the declaration, there's the identifier, which names the variable, and then there's the numeric literal, which is its value. Then in the while statement, you've got the condition, which is just a binary expression in this case, or a binary operation. And its left operand is this identifier right here, counts. Its right operand is the numeric literal, and the operator is just less than. And then you have the body, which in itself is a subtree. So yeah, if you have the AST of a program, you can run it by walking the AST. So in this example, if we were to run this program, we would first start at the root, and then we would visit the variable statement, and then we would visit the variable declaration list, we would visit the variable declaration, and once we get to this point, we know that we have to store a variable in the current scope. So we need its name, we need the initial value. To get the name, we're going to traverse the first child, which is the identifier, and we see, okay, it's called count, so report back to the variable declaration, so walk back here. Then we get the value, so we go to the second child, the numeric literal, and we see it's a 0, so report back. Now we know what the name is, we know what the initial value is, so set count equal to 0 in the current. And we're done executing the variable declaration. We backtrack up here, we're done executing the variable statement, and then we backtrack all the way up to the root in preparation of executing the next statement, which is the while loop. So to execute a while loop, you would execute the condition, and then check if it's truthy. If it's truthy, then you would execute the block, and then you just repeat this process until the condition becomes falsy. Once it's falsy, then you're done executing it, so you backtrack all the way up. So to kind of like exemplify this, we visit the condition, which is a binary expression. In order to evaluate this, we need to know what the left operand is and what the right operand is. To figure out the left operand is, we're going to visit this identifier. We see its count. and we can just query the place that holds the variables for count, and we're going to get 0. So report back to the binary expression, left side is 0. Now you got to get the value of the right side. This is this numeric literal, which is a 10. Report back. So left side is 0, right side is 10, and then just apply the operator to those two operands, and we see that the result is true, which is truthy. So walk back to the while statement node and report that value. And because it's truthy, we're going to execute the body. So we visit the block, and then we just visit like all these nodes down below, and then we execute it. And then once we're done executing that, we go back to the while statement, and then we visit the condition again. Then we execute it, and then when we go back here, if it's truthy, then execute this. But if it's falsy, then we're going to finish executing the while statement. We're going to traverse back. We're going to backtrack up to the root. And then we're going to try to visit the next statement, but there is no next statement, so we're done running the program. All right, so an interpreter that does this is called an AST walking interpreter. Name kind of gives it away. This is probably the easiest type of interpreter that you can write. So for now, we're just going to focus on parsing the set of tokens into an abstract syntax tree, and then in the next part, we're gonna walk the tree to actually run this thing. Okay, so before parsing, we need to specify the syntax of our language using a bunch of rules called productions. So this is an example of a production. And all this rule says is that whatever's on the left side, so if statement, can be broken down into whatever is on the right side. So in general, a production is just on the left side you have one, it's called a symbol, and then on the right side you have a list of symbols, and the symbol on the left can be broken down into whatever is right. So symbol in this context is not to be confused with these symbols. They're a little bit different. Excuse me. So let's do another example. Let's do a while loop. So a while loop can be broken down into the while keyword followed by the expression in parentheses, which is and then a block of code. So there's two types of symbols. There's terminals and non-terminals. A non-terminal would be like a if statement, while loop. These are things that can be broken down further, and then terminals, like ifs, like this if keyword or this while keyword, are things that cannot be broken down any further. So terminals are basically tokens, and non-terminals are like more like sophisticated constructs, I guess you could say. Now that we have two statements, let's define what a statement is. So a statement can be broken down into either an if statement or a while loop. And then we have a block. We actually use block without even defining it first, but let's define it now. A block of code is just a list of excuse me, it's just a list of statements. And the star right here just means that that statement can occur 0 or more times. And now we have to define what an expression is. So expression, I think for now we're just gonna set it to either true or false. Later on, we're going to add in the operators. That's going to be like included in the definition in the definition of expression. But for now, we're going to keep things simple. Actually, I'm going to introduce another symbol called atom, and I'm going to say that an atom can be broken down into true or false. So these are all like productions. Each of these rules is a production, and the set of productions is called a grammar or context-free grammar. There is a rich theory underlying like the stuff, but we're like gonna skip the theory and just jump into the practice. So to actually parse these things into an abstract syntax tree, we first have to associate a node with each of these symbols on the left side, or each of these non-terminals. So let's go ahead and create some AST nodes, or other types of an AST node. So for a block, a block is just a statements, and a statement is either an if statement or it's a while loop, and an if statement interface statement. So for now, we're not going to support any else ifs or else. We're just going to have a condition, an expression, and a body, which is a block. And I think we should also give these things some types, just to like disambiguate them. Actually, let's capitalize this. Type if statement. Statement, and then I think I'm going to introduce the Boolean literal, which, sure, let's just do that, and then we'll say an expression is Boolean literal. All right, so now we just need the while loop interface, while loop, and we have a condition, we have a body. All right, so this is going to be the first iteration of our language. It's extremely simple, and it's also simpler to parse, as you'll see. So to parse this, we're going to use an algorithm called recursive descent. How recursive descent works is that it associates a function for each non-terminal. So we're going to have this block function. We're going to have the statement function, if statement, while loop, expression, atom. And each of these functions is responsible for constructing the AST of its non-terminal after consuming just the right amount of tokens from a starting point. So let's look at an example. So let's just say that this is the program that we're trying to parse. After tokenization, there's going to be this end file right here. And let's just say that our starting point is the thing. And we're going to call if statement on it, because we're going to try to parse this thing into an if statement. So this token, the starting point, is what we call a look ahead. And we can essentially read off the if statement's production, how this function is going to work. So it's going to consume the if keyword. Let's remove that. So we consume the if keyword. And then it's going to consume the open parentheses. Let's consume that. And then after that, we get to an expression. So we're going to, and this expression is the condition of the if statement. So we're going to get the AST nodes from this expression function over here. And so this expression function expression can be broken down to an atom. So we're going to get the AST node from the atom. So we return whatever atom returns. And then this atom is either true or false. So at this point, like the look ahead is true. So we're going to check, okay, if the look ahead true, then we're just going to, I guess we're going to consume it. And then we return like the Boolean literal with value set to true. And then if the look ahead is false, then we consume like false. And then there is another possibility where the look ahead is neither of these, and then we throw an error. Throw error. So there are we'll talk about syntax errors in a little bit, but so like once we get to this point, the atom is going to consume the true, and then it's going to return one of the. It's going to return. Sorry, this should be false. It's going to return this, and then expression is going to return this, and then we'll have the condition, which is just Boolean literal right here. So then we can keep consuming. So after we skip over the expression, we're going to consume parentheses, and then we consume this. and then we're gonna get the body to block, and we'll talk about how these two works in a little bit, and then we consume that. So all of this kind of gets in the process, and then this while loop is like really similar too. We consume while instead of if. Oh, and also we've got to return something. Return the if statement here. We got to return the condition in the body, and then here we also while loop. All right, so let's talk a little bit about syntax errors before we dive into how these two. So let's bring back our example through. So let's just say we try to parse this into an if statement. We're going to consume the if, but here we have a problem because we want to consume the open parenthesis, but we actually have a true here. So if we try to consume a token and the current like token is not actually that one, then there's going to be a syntax error. So we're just going to throw an error like at this point. Now there are ways to like do syntax error handling a lot gracefully than that, but it does add complexity, and we want to be as simple as possible, or we want to stay simple. So we're not going to like talk too much about error handling techniques. Yeah. Now let's talk about how the statement is going to work. So this statement is either can either be broken down to an if statement or a while loop. And also, let's bring back this example. Instead of like trying to parse this as a if statement directly, let's just try to parse this as a statement. What will happen is that we have to make a decision. Are we going to parse this into an if statement, or are we going to parse this into a while loop? Well, we're only going to parse this. We're going to parse this into an if statement because the look ahead is an if. So if we try to parse this into a while loop, what's going to happen is that we're going to try to consume while, but the look ahead is if, and so there's going to be an error. So we can only parse into an if statement. So the way that statements are going to work is that if look ahead, if then we're gonna like well, if we're just gonna return if statement, and then if the look ahead while, then we're gonna return the while loop, and then if it's neither, we just throw an error. Now for block, a block. Oh, I guess we yeah, actually that's fine. That now for block, a block is just a list of statements. So we need to have the statement list, and then we kind of have to like have a loop somewhere to like put stuff into the statements list. So the question is, what is the terminating condition? The terminating condition is just when we get to a token that cannot be when we get to a token that is not the start of any of these statements. So if we get to a token that's neither an if or a while, then we're gonna stop. In other words, if look ahead is if or it's a while, then we're just gonna like add statements, and then if it's it isn't either of these, then we're just going to return statements. So that's how like these recursive functions are going to work. And when we try to parse an entire program, what we want to do is parse it as a block. So this block is what we call the start symbol because it represents the entire program. And when we want to consume every token until we get to the end of a file. So let's go ahead and code this up. And I think I'm just gonna keep this for now, just as a reference. So what I'd like to do first is I like to create this thing called a token manager. So let's create this, and this is gonna help us consume tokens, and also throw errors. So this is going to take the tokens list in the constructor. And this I is just the current token that we're on, and anything before the I is all the tokens that we've eaten or consumed. This peak is just going to return the current token. I'll return this. Now I'm gonna have this eat function. I call it consume here, but I'm gonna call it eat over here. And this is gonna take in token type. Either gonna take in a single token type or a list of token types, and then it's gonna check. It's basically going to check if like the current token that we're on, like at index I, has the same type as one of these that we passed in. And if it does, then we consume it. And if it doesn't, then we're gonna throw an error. So we have to first if the types is actually a string, then we're gonna have to turn it into an array first, and then types. So here we're just checking if the types includes the current token type, and if it doesn't, then I guess we can say expected types, or just say this. All right, there we go. Oh, I guess we have to include. We have to have this thing. We have to have this type called token type. Either a keyword type, identifier, string, it's a number, one of the symbol types, or it's EOF. And why do we have this? The error. All right, this should be type. Okay, now let's work on our parser. Parser is going to be a class, and it'll take us input in the constructor, the token manager. So tokens manager, read only token that. Right, and let's just create our functions. We don't have to implement these right now, but just to put these in here. Payment, while loop, expression. Whoops. Atom. All right, so I also like to create these helper functions called the statement look ahead. Help us like identify when for a particular look ahead that it matches one of the ones for statements. And so the look ahead only matches for statements if it either matches the if statement or the while loop. So let's have two more functions here. Is if statement, while loop, look ahead, and all of these are going to take in tokens. Did I export the token? I guess I didn't export this. Let's export this. Type here. And usually I get the AI to fill like this out, but I actually hit my limit today. All right, so all this does is it just checks if type is equal to while. This one, token type is equal to if. This is while loop head, or is All right, so actually in the AST node, we also have to export all of this stuff. Whoops. I think I'm also gonna make an AST node type. AST node, just either a statement or an expression for now, and leave it as this. We also need to give each node an ID. This is going to help us with the debugger. It's not like strictly necessary right now, but we will as well just early base base node D, and we also need a location, so we can just piggyback off the location that we have in the tokenizer. Okay, there we go. And for generating these IDs, they have to be unique. I'm just gonna do this. This is like a quick and easy way to quick and dirty way to generate a unique ID. Whoops, not just ID, just ID. All right, there we go. So we've exported all of this, and now we're ready to work on the parser. This is gonna block. Let's type here. And if statement a loop expression atom. Wait, do I have an atom type? Actually, let's go ahead and make an atom type. Because later on, we're gonna have more atom types than just booleans. We're gonna have like strings, identifiers, and so on. Atom is basically the like the simplest unit in an expression. It's not like an operation. It's just something that represents like a value by itself. Okay. I guess we could export this. Actually, we have to export this. Need it here. Okay. So block. Need a statement list. Well, so we're just implementing this, implementing logic. The great thing about like having like the pseudocode here and having planned this out is that translating this into code is like pretty straightforward. Statements, push, statement, and we need to uh, return the node as an ID, that has a block, and that has statements, and we wait, what happened here? I need to write statement. Oh, I meant to write statements. There. Okay, so we need a location here. I guess we can do the location a little bit later. I'll have to worry too much about that now. And for statement, it's look ahead. I guess we'll just call it token. We'll just call it look ahead token. Peak. Okay, so if the if it's if is a loop ahead, just return loop. If it's a if statement, so is if statement look ahead. Start the if statement. And I guess if it's none of these, we just throw a new let's say unexpected token. Token.type. And the way that this if statement works, copy paste this, or rather move this code in here. tokens eat if eat open parenthesis addition expression eat body. Okay. While loop is a thing. While this is while. And then expression is just return this dot atom. This dot atom. So if token type is equal to true, or token dot type false. Actually, let's just do this. True. Implement this verbatim. We return ID, UID, type Boolean literal. The value is true, and we don't worry about the location. Now, type now this is false. This false here. If it's neither, then we throw error. I guess we can just say unexpected token. Type. Okay, so we should be able to parse programs that fit this description, or rather, we should be able to parse programs of the syntax. So let's try it. Did I export the token? Okay, I exported the tokenizer. I exported the manager. Let's export. I exported the parser. Okay, so in the main file, our hello program from the beginning. Actually turn this into the full parser. So program is. Let's try this one. Well, I guess actually we're missing something here. In the parser, we need a function called parse. And this is going to return a block, and it's going to do this. Yes. But actually, in the parse function, whoops, program. In the parse function, we actually have to consume the end of file token. I'll explain why we have to do that in a little bit. All of these should be private. We only want the external world. Call this parse function. So here's our program. Here's tokens. There. Nice. New tokenizer.tokenize. Probably tokenize. I have to do this. Manager. Let's just do this. Token equal to token manager. Hold on this. All right, let's create a parser. Parser. Token. Let's parser parse. Let's see what happens. Okay, so we have an error here. Why do we have an error? So we try to parse the block. We try to parse this. I parse the if statement. And we get to here, so this dot expression. That's because we didn't consume anything. So tokens.eat true. Tokens.eat false. Now I think it should work. Copy paste this into a JSON file and see if it holds up. So here we have a block, we have an if statement, have a Boolean literal set to true, so that corresponds to this. And then we have another block in this one. Yep, so this was correct. Let's now try to parse a more data program. So let's, I guess we add a bunch of like random file true body here. Let's add a bunch of nesting. If false, I guess this can be empty. If here, this can be empty, and then let's add an if statement. Here, this is really poor formatting, but we're just testing a parser. So if true, let's put a while loop inside the body of an if statement now. Let's parse this and see what we got. So at the very top, we have the while loop corresponds to this one, and then as part of the body of the while loop, we have the block. And this block has one statement, two statements. The first statement is this while loop, so this one. And the while loop's condition is Boolean literal, it's true, this one. Then it's got just the if statement in the block, which is this guy right here, where the condition is false and the block is empty. All right, very good. Now moving on to this if statement, which false in the condition and empty body. And now this if statement down below, this one right here. So it's true for the condition. And for the body, we have a while loop. The while loop has a true in the condition and an empty body. Okay, so I think this parser is correct. Let's go ahead and add the locations. And hopefully the locations will be quite straightforward. So let's start with a block, or with the block, I should say. So the location of the block is going to depend on whether statements is empty or not. So if the statements is not empty, then its starting point is going to be the starting point of the first statement. Starting point of the first statement. Okay. One.log.end. I'm not sure why I put this question mark here. Now, if it's empty, if the block is empty, it doesn't really matter like where we put the location, but we're gonna set it to the location of the next. And that's the location block. Now for the statement, well, we don't really need to create one for the statement, but here, if statement is the starting point is just the starting point of the if token, and then the end, just the end of this token, any point of that last token. Whoops. The while loop, we have to start here. Block. And start block. So for the atom, this is just going to be the token location. Token.lock location. And let's go ahead and test this program location. And I think this one's going to be a little bit more annoying to test manually. So I'm just going to briefly look at it, and I'll probably just get the AI to check it over. All right, so I checked it, and this is correct. I'm going to return to this part, explain a little bit why we need to eat this end of file token. Because if we didn't eat this, let's just say comment this out, then what would happen is that somebody could just put some random stuff like over here, let's say this, and then if I parse it, then this would like actually parse, but clearly like there's a syntax error here. So if I uncomment this out, then we're gonna get this error, got end of file, or expected end of file, but got this. So that's why we need this end of file here. Now let's beef up our language. We're gonna add support for else ifs and else in the if statement. And let me go ahead and delete all of this. So we can have any number of else ifs and an optional else. So this question mark just means that the else is optional. And an else if is just going to be, yep, it's going to be exactly the same as this, except there's an else over here, and the else block, that else, and then a block surrounded by the two curly braces. So let's move this to the side, and now we have to update our AST node. Have a bunch of else ifs. If add this interface. Actually, let's add the else. The else could just be a block. We don't really need any more information. And this is optional. It should be an array because we can have any number of them. So let's if addition and body. Yep. Now in the parser, let's go back to if statement and go ahead and find the else ifs. So we need this, and let's type this array if and then else brand. Either block or it could be undefined because it's optional. And while the token or the current token is an else, you guys spelled wrong. We're gonna eat it. Else. Now we have to check if keep spelling this peak wrong. But now we have to check if the next token is an if, because if it is an if, then it's an else if. Otherwise, it's an else. So here's a situation where we have to look another token to it to disambiguate whether it's an else if or an else. So yep, let's eat this. Get the expression. Or actually, let's make this a bit less ambiguous. Else if condition. All right, so there's our if, or there's our else if. So we're gonna continue this loop whenever we encounter an else if, and this block is going to be responsible for eating the tokens and constructing the. I guess this is not really a node, but it's going to be constructing. It's going to be constructing the else ifs. But once we hit a token that's not an if, then we will try to parse it as an else right here, and yeah, we're gonna break like once we parse it as an else. If we don't break, someone can put a bunch of else's like someone could put something like this. If true, else, else, and let's say there's a while loop here, then this is clearly not correct syntactically. But if we don't have the break here, then somebody could do this, and then whatever is in here gets discarded. So we need the break statement. But we also need to track the location, because if there is else ifs and there's an else, then the end is not necessarily going to be the end of it's not going to be here anymore. So we need to update the end. Give it the else ifs, the else branch. Okay, so let's go ahead and test this out. Let's have an if true, else if false, else. I guess we can add another else if, but let's stuff in the body on this one. We'll just do that. And let's have an else branch here and run this. Whoops. And compare the AST. I'm just gonna look this over briefly. I'm not gonna go like I'm gonna look it over like too carefully, because we'll do like more testing once we have all of the statements done. All right, so at the top we have this else, or sorry, the if statement, and let's collapse it. Yep. So there's only one statement here. Then within the if, we know that this part is correct, empty block. Let's check the else ifs. How many else ifs do we have? One. We have two. Okay, so we have two else ifs. Pretty good. And then we have the else block here. There's nothing in it. Let's check the body. There's nothing in the first body that corresponds to this one. Then in the second body, here's the second one. I didn't bend it. Here's the second one. There's a true for the condition, and then there's the while loop with a true condition and an empty body. Okay, so let's test. Let's add some stuff to the else right here. What do you want to add here? Let's just add another if statement. Body. Let's also add a while loop on this. Copy paste it. See what happens here. And I think we can just collapse. We can just collapse the first else if. Didn't really change. We can also collapse the second. Also, we can actually collapse all the else ifs because it didn't really change. Here, we have okay, so we have the block, then we have the two statements, and the first statement is the if statement, true over here, and an empty body, and the second statement is for while loop. So this is correct. Now I'm going to do one more test. Actually, I'm going to do two more tests. One, I'm going to remove all these else ifs. Just have an else. This parse correctly. Okay, so there's the if statement at the top level, and here's the else if. There's nothing in here. That's good. And then the else. There's the if statement. Yep, empty body, and the while loop. And last test I'm gonna do is just this just to make sure that we didn't mess up parse. But there's no else ifs or else. So there's the if statement, there's the true Boolean literal, and there's the block. All right, so there we have the if statements with else if and else support. Let's go add function declarations. And a function declaration in this language is going to start with the fn keyword. So function declaration. It's going to be the fn keyword, an identifier, the open close parentheses, and in it is going to be params, any number of them, and then followed by a block. And params is going to be an identifier, or any sequence of comma and identifier. And I guess we can also add an optional like comma at the end. JavaScript supports this, a bunch of different support this. So let's go ahead and actually let's add the return statement as well. It's going to be a return keyword followed by an optional expression and the semicolon. So let's put this line here. It's either statement is either function declaration statement now. And I think I'm going to parse the return statement first because this. So up here we need to add the return head. Token. And we can also add the is function declaration look ahead. Okay. Where's the statements? If the token function declaration look ahead, return the stuff on declaration, which we're going to import a little bit. Let's implement this first. All the way down here. And we have to add an AST node for both function declarations and return statements. So the return statement is going to be pretty simple here. All it has is just a type and then expression, but this expression has to be optional. And then we have the function declaration. Function declaration, which, yep, so type is function declaration. We have a name, we have a list of parameters. Now here, we could make the parameter, instead of making a string, I guess we could introduce the identifier AST node, which I think I'm going to do because we will need that once we expand the atom to include identifiers. So let's introduce the identifier AST node. Identifier. Yeah, that was good enough. And go make this identifier. Here we just consume the return token, and then we try to parse an expression. But actually, because the expression is optional, we can't just do this. We need to check if the current token dot peak is. We need to check if this is an expression. This expression look ahead. So we don't have this function yet. We're going to implement it in a little bit. Now let's return the ID or the node. I mean, type. One to implement this. So for the is expression, look ahead. Because our expression is an atom, we also need an is atom look ahead. And here it's just I guess this true and the false are both primitives, and when we add in the identifier, it's also, I guess we could also consider that primitive. So head just to be like just to prepare for what's about to come. At this point, true or false, sure. I guess we might as well just fill all this stuff in, even though like we haven't added null or number or any of that stuff yet. And this atom look ahead, yep. So that I guess let's just make type is an identifier. We can just return is atom look ahead. Date. Export this. Hit op. This floppy here. Go. Now the function declaration. Eat that. And then we eat this. And then we need to construct the params here. But I think I'm going to use a helper function to construct these params. So first we check, okay, if this.tokens peak, if the type is identifier, then we know that there's going to be a params list. This identifier, list of identifiers. We're going to return identifier list. We're going to eat that. We're going to eat this. Get the body, and then we have to eat the last token, get its location, and that's going to be the function declaration node. So we have the type, we have the name, we have the params over here, and then the body obtained here, and there's the location. So now let's actually let's simplify this a little bit. Params. If it's that, then this params. Otherwise, it's we don't need this if statement here anymore. And name fire that eval here, and we have to cast this. We export this. We didn't export this. Our token. Actually, let's go back to AST. Let's not call this val. Let's just call it name. Now for the params. So it's a parameter list. So we need the first parameter is equal to that, and then we have this parameter list. And we're gonna have to create the AST node, add this first token, which is just gonna be this. And also let's type this better. And also let's call it identifiers instead of params. So now we need to check if the next token is a comma. If it is a comma, then there's two possibilities. Either there's an identifier that follows, or there's another comma that follows. If there's no identifier, or rather if there is an identifier, then we're going to keep looping. And we're going to keep looping until there isn't an identifier anymore to the right, in which case we must be over here. So while this tokens type the comma, then we will eat this. And we need to check. We can't do this yet. We have to check if the next token is identifier. Yep. I think I'm gonna call this next because it's next to the comma. And we just construct the identifier based on this token. Now the else condition, the else is well, actually on the other hand, we actually don't need an else because like this condition is not gonna fire if we're in this case, and then whatever is to the right of it is not going to be an identifier. which is the current token that we're going to be on. So this is not going to evaluate to true, and so the while loop actually breaks out. So this is actually all we need. Identifiers. We have some type errors. Where's the type errors? Turn this to function declaration addition. I think I forgot to add. Where's my statement? Yeah, I forgot to add the function declaration, the return statement, to this type right here, and that's why we had so we had the type error, statement while loop, and I spelled params wrong. Oops, params wrong here. So that should be good for our parser. Let's go ahead and test it. And I'm only going to do one test. fn main, or I guess fn add. Let's just follow the AI suggestion here. We can't return that, unfortunately, a plus b, because we haven't supported operators yet. So I think I'm just going to return true. And let's just have a if statement here for good measure. Let's add another function declaration down below. Yeah, we can do sub. We're not subtracting anything, but just call it sub anyways. Here, let's have a while. Actually, let's put the while after the return. When we talk about program execution, this is actually going to be valid, but we're just not going to execute the while here. And to trip the parser up a little bit, let's put a function, or let's put in a statement at the end of it. Okay, so parse. The requested module does not have an export. I think that's because we didn't mark this as a type. Yeah, we didn't mark this as a type. Okay, now we can parse this. Load the AST into the JSON and just compare. So actually, I'm going to check that we have 3 statements at the top level. So if statement, declaration, yep, declaration name is correct. We have 2 identifiers. We have this, and we have A and we have B. And then in the body, what do we have in the body? We have the if statement, true in the condition, and an empty block, no else ifs, and no else. And then we have the return statement where the expression is true. Now we have the sub function. We have A for the first identifier for the first parameter, and B for the second parameter. Up there's the return. Return comes first. False. While loop comes last with an empty body. And now there's the if statement. Actually, I'm going to do one more test. I was going to test it once, but I do want to check that the return with no expression can be parsed correctly. But we'll just I guess we can also put a comma here. Chip it up some more. Oops. So here's the function declaration. We still have the same number of identifiers, and they're named the same AB. And then we have the return. There's no expression. So this is correct. Okay, let's go add some primitive types, or add them. So we only have booleans right now, but we also need strings, we also need numbers, and we also need identifiers. I guess, yeah, let's just add these. For now, we do need the parenthesis expression as the AI suggested, but we can do that a little bit. So go to AST and add in the nodes, numeric literal, and then string literal. And we have the identifier. So actually, I'm going to introduce their type. And actually, I'm going to group this. So, and I'm going to be a primitive. Put it below, actually. And this is just going to be, these could also be an identifier or a, oh yeah, we've got null. Got to put null. Put null at the beginning. So we should have the null literal. It's going to be null literal. Boolean literal, and string literal. Let's move up a little bit. And lastly is the identifier. And could be primitive. Okay, so that should be it. Save the syntax. Go back to Parser. Let's go add the private in front of these, or we actually parse the atoms. Where's the atom function? Here's the atom function. So now we just like look at all these token types. We can't encounter a null. Then we need to create the null literal. Yep, the location is correct. If we encounter a number literal, then we create the number node. So we just number, and we just turn AST node literal. String literal is next. Strings. This part is pretty mechanical, so I'm just gonna follow the AI suggestions. And I think we have all the literals. We have the booleans. We have the null. We have string. Okay, yeah, we have all the literals, but we need the identifier. And then we just return the identifier. So all of these, like all the stuff inside the if statements, look like pretty much the same. And I think this one we don't actually need. Yeah, we don't need to cast this as a number. It's already a number. Yeah. Okay. We're ready to test these. Let's this if null, and we're just gonna use a condition of the if to test these literals. So or parsing of these literals. So if null, if true. I guess we already tested true or false. We don't have to do the booleans anymore. Let's test a string. Let's test a number. Test a decimal number. And then let's test an identifier. Of course, if you run this, this is not going to work because ABC is not defined. But for parsing purposes, we don't really care about execution correctness. Okay, let's see. If statement, here's a null literal. That's this one. And then the second one is this string literal here. Let's see if it's yep. Okay. Numeric literal. Here's the value. Second numeric literal. Here's the decimal number. Yep, there we go. And then identifier. Okay, cool. Literals are correct, and so are identifiers. Let's go add our last two statements, which is going to be the assignment statement and the expression statement. We need the assignment statement to add variables. But actually, I think we're gonna just set it to expression equals expression because we need to be able later on when we support objects and arrays, we need to be able to modify elements. And we also need to do some checking to make sure that we're actually modifying the element of an array, but we'll do that at runtime. And then there's the expression statement, which primarily is used for calling. So like, for example, like this would be a is equal to 5. That would be an assignment expression. If we had an object dot k1 dot k2, that would be another assignment expression, and so on. And then the expression statement would. Okay, so let's parse this, but before that, we always have to create the AST node. So underneath this assignment expression extend AST node. And this one is just gonna have it's gonna have a left side. So there's left, and then there's right. And again, like not every expression on the left side is gonna be valid. You can't like, for example, assign to a function call, but we're gonna check that runtime. And this should not be AST node, should be base node. And then we just need the expression. Expression statement, and then also this should be assignment statement. And there's the expression statement. All it has is an expression. Not forget to add this, the union here, assignment expression, or assignment statement, expression statement. Now we can modify the parser. But first, let's go and include a look ahead. Or actually, we don't really need a look ahead here. What we do need is to do this. Is look ahead token. This is another one of those cases where actually add this. So this is another one of those cases where we have to do a little bit of parsing, like first, to disambiguate whether it's an assignment statement or an expression statement. Now we can't just look at like a certain amount of tokens like afterwards, because expressions later on when we add operators can be arbitrarily long. So what we do is we just parse the expression, and then we know that it has to be it has to be either one of these, and then we look at the token afterwards, and that's gonna allow us to disambiguate which one it is. So if it's an equal sign, then it's got to be an assignment. We're not gonna support equal operators inside any of the expressions. And then if we see a semicolon, then it's got to be expression statement. So that's why we have this function right here. This either returns an assignment statement, AST node, or an expression statement. Let's add it here, type it, expression statement, or it's an assignment statement. And this one, yep, we just do this. We just check if it's an equal sign. So we get the left side. And if it is an equal sign, we're going to eat that. Eat the right. And actually, we just need to return the node. And then the location is just going to be the start of the left expression. And then the end. Actually, we're missing something here because both of these end with a semicolon. So actually, the end should not be the right. Always check what AI produces. It should be this. We eat the semicolon, and that should be the end on block. So here's end. Put this on one line. Keep the code order in terms of lines. Okay, so otherwise, if it's not an equal sign, then it's got to be just this semicolon here. So we can go ahead and eat that, and then return the expression statement. So here's the expression. That's just the left. And then the location is starts, or the location starts at the left expression and then ends at the semicolon. Okay, testing. So let's do some prints. So very simple. Whoops. This is a call expression which we haven't implemented yet, because right now our expressions are only atoms. We're gonna implement the full expressions last, because parsing those is a little bit different than parsing these statements. So let's we'll just print and just test this flow and see. Oh, we have an error. Okay, so this should have parsed correctly. Why did it not parse correctly? If you ever run into an issue, there's this thing called the JavaScript debug terminal, which you can also open here. And what that does is, if you just set a breakpoint here, and then you run your file, then it's going to attach a debugger, and it's going to pause at the breakpoint. And here on the left side, you see the variables. There's global. Okay, this is probably not that useful because this is like the stuff that's in the runtime. And then there's the module, which is the stuff that you have declared. So in our case, we want to check the token. Oh, that's just a class. That's actually this thing. We want to check our instantiation of tokens to see our tokens array. So we have a string, we have semicolon, with end of file. So tokens looks correct. And I'm gonna go into the parser. Actually, let's go and see where we errored. So token.eat and parser.parse. So we tried to eat an end of file here, but we actually got a string. That means we didn't consume any of the tokens. The problem must have been in block somewhere. Let's just set a breakpoint over here to see if we even attempted to parse the expression. And I can click this button, continue, and that's going to execute code until it either finishes or until it hits next breakpoint. So this breakpoint didn't even get hit. Now let's do this again and see if this breakpoint. Whoops, that's the wrong terminal. We can remove this breakpoint. Okay, so that didn't get hit either. So that means there must be a problem over here, and I think I know what the problem is. We didn't add the statement look ahead, but let me show you one more thing. I'm gonna run this. You can there's this thing called watch, right here. There's also the call stack in case you want to go up and down. But there's this thing called watch, and you can actually like run some expressions here. So uh, let's just do something like let's just run this. Actually, let's just check what the token is. Tokens dot peak, and you see that this is of type string. And so let's run another expression. I want to see like what this returns. So let's okay. So this gives us false. So the problem here is that we don't have we didn't check if it's an assignment look ahead. So we need to check if, or expression look ahead, I should say. We could add is assignment statement look ahead or is expression statement look ahead, but since they all like kind of resolve to whatever the look ahead is for the expression, I'm just this. And we're not going to add any more statements. This is the end of this. We have this fully spec'd. So let's do this. Token. And now I believe this is correct. So I guess we can just run the debugger again just to check. So oh, and also this watch thing, it actually saves. It actually saves, so that's pretty cool. So in this case, we're back at the token, and this is gonna evaluate to true. So let's set a breakpoint at statement. You know, let's set a breakpoint over here. And so we're gonna pause here. We haven't called the statement yet. Now let's call the statement, and we're gonna run this expression because this should be true. Yeah, so that's true. So let's set a breakpoint here. Run it, and then let's go into here. Actually, at this point, I think we could just like kind of run it to a completion. And here's our AST. And I don't think we need this debugger terminal anymore. Let's look at it. And it should only have a hello. Yep. So there's a string literal. There's hello, and there's nothing else. Well, I guess there's an expression statement, but otherwise, like there's nothing else, and that's good. But let's add some more stuff. Let's add true. Let's add null. Let's add. What else do you want to add? I think that's just it. Actually, let's add an identifier. Why not? Let's just add some numbers, and then identifier. Yeah, let's just do that. Okay. Copy paste. Up. Go to here, and check the AST expression statement. So there's string literal, Boolean literal. It's true. There's the null literal. Number literal, and there is this. Actually, am I missing something? I'm missing a primitive here. No, I'm not. Okay, so this is fine. You know, just for good measure, I'm gonna do this. Oh right, I forgot the semicolon. Don't forget the semicolon. And I'm just gonna look at this. So there's Boolean literal. There's false. All right. So that's all our statements done. There's two more things that we need to do. Number one is we need to add our remaining atoms, which is going to be it's going to be the array literal, it's going to be the object literal, because we got to support arrays and objects, and it's also going to be the parenthesized expression. Or I think we're going to do this parenthesized expression. And then the second thing is we have to add our operators and call expressions and access expressions. So let's do the atoms first. We have to define the. Well, I guess we already defined this, so we got to define these two. Now array literals. This one is pretty straightforward. It's just two. It's just two square brackets, open, close, and then in between there could be some values, or it would be like expressions, but I think I'm gonna call it the expression list, and the expression list is gonna look very similar to this, except instead of an identifier, it will just be an expression here. Yeah, and now we have the object literal. Actually, let me move the primitive all the way up here. And then the object literal is going to be two curly braces, and optionally, like there's some key value pairs in between. So I'm actually just going to introduce key value pairs thing, and then this key value pairs. Yeah, so let's actually do this. So key value pairs also looks like very similar to this. It's basically just a key value pair. I guess all of these like list like things, like params here are gonna look similar. Then there's the key value pair itself. So I think for this, we could make it an identifier, but I think we're actually going to um allow it to be any primitive. So actually, let me just check the primitives. Yep. So it could be any primitive, or we could also compute an expression first, and then whatever the result of the expression is will be our key. Kind of like in JavaScript. Like, actually, let me just finish this first. So in JavaScript, you can do something like this. And let's say we had a function here, foo, and it does something, and then returns something too. So you could like do something like this, foo, and then like 15 or something. So we're gonna allow this to occur. But if it's a primitive, then we're just gonna coerce it into a string, and then whatever the string format, whatever the string value of that primitive is gonna be the key for the expression. Let's create the AST nodes. So we need one for each of these. Let's make the parenthesis expression AST node. Easy. Where the atom. So here expression type parenthesis. So this is all it is. It's like pretty straightforward. Actually, it's an atom. So in this union, then there's I'm going to introduce this thing called reference type. It's not exported right now. Type ref type. It's going to be an array literal, or it's going to be an object. Literal, array literal. Literal is just going to be like a list of expressions, and those are going to resolve to values. And then for the object literal is a bit more. We need a list of key value pairs. Type. And I think for the key value pairs, I'm just going to make it a list of pairs, and I'm going to introduce this key element here. So type key, and this is either going to be an expression key or it's going to be a primitive key. And then if it's an expression key, and that's just going to be an expression type key, and this is going to be expression. I'll explain a little bit why we need to disambiguate these two in a little bit. So primitive key. Or actually, we don't really need primitive key. We just need identifier key. Type our key and name is string. I guess we can just give it the identifier. And then the KV pairs, I guess we just call it pairs, would just be key and expression. But why do we need to disambiguate these two? Well, if we I'm gonna just make a JavaScript file real quick. Yes. So let's say we made an object, and then we had foo, and this would be like, I don't know, 5 or something. And let's log this. So this is gonna give you foo, but let's say we added foo is like, say, key. Now this is still gonna give you foo, but if I did like this instead, then it's gonna give you some key. So for identifiers, we need to decide whether to evaluate as an expression or just to take the name. And so if we're gonna take the name, then or rather like these two like distinguishes whether we take the name or we need to evaluate as an expression. Export the ref type and also put it in the put this as expression. And we also I guess we put the parenthesized expression here. Actually, we should put the ref type over here. Let's do this. Need it over here anymore. Now, what happened? Not exist on type atom, right? We forgot to extend something. There's parenthesized expression. Yeah, we didn't extend the base node. base code, and no type errors fixed. Let's parse. What do you want to parse first? Let's parse the parenthesized expression. I think that one's like pretty easy. So parenthesized expression, and this we're just going to consume that. Open parenthesis. Let's close this. Like to respect from this. Get the expression, and then consume that or eat that, and then just return the parenthesized expression node, which is this. Here's if token.type is equal. And we just return the parenthesis expression. We also need to like update the look ahead here. So if is Atom look ahead or token dot. And might as well just add these. All right, so that's parenthesized expression. Yep. Now we do the. I guess we can do the array literal first, and then we'll do the object literal last, or array literal second, and the object literal last. Play literal. So this array literal we just eat. Yep, we eat that, and then I guess we can add an expression list. Expert list. We're also gonna need this when we start adding function calls, because the arguments to a function call is really just expression call. As well just add this right here. So expression list const expression. Yeah, I guess we can do it first. Is an expression. Here's the expression list. So just like how we did params, we have this loop right here. We eat this token, and then as long as what's to the right of this comma is looks like an expression, then we're just gonna try to parse it as an expression, and then we terminate. Once we skip this comma and the right side is not expression anymore, we can just return expressions. And now we have to get the, did we call it elements? Very literal, yeah, we did call it elements. So elements is going to be, we have to check, okay, so if is expression look ahead, this tokens ups a little bit, so we get the expression list if there's some expressions in between the two square brackets, or if there isn't, we just make it empty. And there it is. There it is. That's our array literal done. Now object literal. Actually, let's do this first. Where's the atom? Here's the atom. Array list. And yep, we can return the object literal here, but now we just need to implement. So how does the object literal work? Oh, we're going to introduce this a little bit more. Let's close this. We're going to introduce the KV pairs helper function just to help us construct the KV pairs. And this is going to be, I think I may want to export. Where's object literal? Here's object literal. I think I'm gonna export this. I typed that wrong. It should be it should be an array of these things. Okay, so this is going to return an array of KV pair. And then we have this KV pair. It's gonna return our KV pair. And let's also make these private. List object literal pairs. Okay, so how do we parse object literal? We get the start, and it'll just eat this. And then we check. Okay, so is it a KV pair? Look ahead. So actually, let's add this function. And here's token. So it's a KV pair look ahead only if it's a primitive. So look ahead. Okay, this is not correct. We go here. Yeah, so if it's expression, actually it should be is primitive look ahead. So turn. Or is it square bracket? So if this is a KV pair look ahead, then we're gonna try to obtain a list of KV pairs. Otherwise, it's the empty array. And there's the end, and there's our object literal. So it's just got pairs. And here's the type. And so KV pairs, this is gonna look extremely similar to the expression list. First, there first. Okay, so yep, exactly like very similar to this. But this one's a little bit more interesting because we need to check if it's this or if it's a primitive. So if let's just call it token, or let's call it key. Yeah, so key. I guess we could introduce this helper function called key as well. But I think that's a little bit overkill. So let's not actually do that. We're not trying to. We're not gonna have a loop in this KV pair helper because there's no like there's not like looping or anything. So the interesting part is just how do we figure out whether it's a primitive or it's this, and that we just check if the token type is a square bracket, opening square bracket. So if it is an opening square bracket, then we know the key has to be an expression key. But we can do this. Let key export these. Our key, and so this would be so if it's an expression key, we need to eat the square bracket, and we get the expression, or I think we should do this actually. What is this? Right, type key and an expression. Type here is identifier key, and what was the identifier? Dot eat identifier token here. This. Oh, it's actually an identifier. Whoops. Let's actually do this then. All right, so that's gonna give us our key, and then we have to consume the colon and value, and that's gonna give us our key value pair. Let's do some testing. Let's. I just realized I actually forgot to test the assignment statement earlier. So let's make an object first and bar. Whoops. Oh, actually, that's not a valid string. Or now let's run this. No main.ts. Check AST. Actually, go ahead and delete this file. Right. So okay, we have the assignment expression. Identifier is A on the right side. We have the object literal. That's good. We have the identifier. Or rather, we have the identifier key, and then this is the identifier. And on the right side, we have the string literal set to bar. Okay, cool. I'm just gonna test a bunch of primitives. Let's say df, and if it's a primitive, it should actually parse as or a non-identifier primitive, I should say. It should actually parse as an expression because we just go and evaluate the primitive as a literal. Yeah. So 1, 2, 3, and of course, like we could do like something like this. Oops. Like we might do something like this, 2, 3, but we're gonna check at runtime whether your keys can actually be coerced into strings. So this is gonna throw an error at runtime, but it's valid like tactically. So anyways, I digress. Let's test this. False, false, true, and I'm just gonna add null, 2, 3, and then let's do like this, 5. A bunch of A's, and then run this. And we have an error expected identifier, but got string. I think this is the problem. So let's make a minimal repro here. Yeah, so this is the problem. Why is there an issue? Oh, right, because like if we, it could be a primitive here. So how do I want to fix? Okay, I think I'm going to abstract out. Where's Adam? I'm going to do this. And this is going to return the primitive type primitive. Here's that. So it's a null, boolean, string, for identifier. I probably should have done this earlier. But let's just go ahead and copy paste this first. And then let's copy paste all this stuff all the way up to identifier. Do I have a is primitive look ahead? I guess we can throw new error here. Unexpected token type. And now we need a look ahead. Is primitive look ahead, or I guess we don't need a look ahead. So Atom is primitive look ahead. Return primitive. Okay, now I think this should. No, it's not gonna work yet because we haven't fixed this part. So at this point, we want to parse this as a primitive. Let's go back to our syntax. We want to parse this as a primitive. And then we have to do a switch here. So if the key prim type is equal to identifier, then we can just return, or we can secure this. Prim.type, name location, this will just be prim. Now, if it's not an identifier, then we have to set it as expression key, and the expression is test this. Good work. I did delete a bunch of these keys. So let's see. So identifier is a, yep, object literal. There's foo, bar, expression key. Actually, let's check the key. Yep, this is identifier key. This is expression key. String literal, number literal, 1, 2. Let's bring back what we had before, and I'm purposely not putting the comma here. Okay, check this AST. Assignment statement, identifiers, a thing right here. Object literal, so we still have this foo as the key. It's still an identifier key, and then we have this bar as a string literal, ASDF, number literal, 1, 2, 3, true. Yeah, so this is going to get coerced into a string when we actually create this in memory when we implement the executor. But the parse is correct, so boolean literal, and then we have the false as the key, expression key, boolean literal, expression key, null literal. Yep, number literal. Okay, so let's try some arrays now. Actually, yeah, let's try some arrays. Actually, before we try arrays, let's try some of these. Try this. So b is equal to 15. We don't support like we haven't implemented the expressions yet, so not a whole lot that we can put in between. these two. But I suppose we could do this. We can like test parenthesize expression same time. And let's make the right side like 15. And check this. Whoops. Finishing changes for that. Here's assignment. This was B. This is the first assignment set to 15. So let's skip that. Object literal. Okay, so here's the parenthesized expression. So it's good to know that we parse parenthesized expressions correctly. Identifier is B. Number literal is 15. So it looks like that works. Let's wrap this. And then we'll test arrays in a second. So identifier, here's the number literal, but that's for B. 15B, A is the name of the object, and here's the expression key with identifier B. So in this case, we're going to evaluate B as an identifier. We're not just going to take the name and put that as a key. And then the literal is also fixed. That's good. Let's do some arrays. A is equal to 1, 2, 3, 4, or 1, 2, 3. With comma afterwards. Oh, okay. I forgot the colon. Okay, there's the assignment, there's the array literal, so elements 1, 2, and 3. I guess we could make here. Why don't we just test some objects in this array as well? Let's go ahead and remove elements beforehand. We can have like pretty deeply nested arrays and objects. Let's say foo, and let's make another array, and let's say 2, and then let's make another object, and here's bar 3, and then as, yes, or baz 4. And this is the last thing that we're going to test before we move on to expressions. Okay, so A, identifier, array literal. We have 4. Now we have an object. This is the second element, array literal. Have an identifier, key, which is foo. The array literal, yep, number literal. So that's 2 right here. Then we have another object, and inside this object, how many pairs do we have? Let's go ahead and check. So there's 2 pairs, which is the right number. We have the identifier key, right, a little bit. There's the bar. Yep, there's the bar, and there's the number literal, which is the value, as number literal, which is the value. All right, cool. Okay, we're almost done with the parser. The only thing to add now is just support for the various expressions. But let's get started with binary expressions. And for simplicity, let's just assume that we only have this multiplication operation. So this is an expression where there's only multiplication. Now we want to evaluate multiplication left to right. So we want to do like 2 times 3 first, and then we multiply the result with 4. So the binary, or rather the AST node that we want would look something like this. So the left child of the binary op would be another binary op, and it would have like 2 and 3. And I guess we could put a multiply here just to like kind of keep track of the operator. Multiply. So when we evaluate this root level binary op, which corresponds to the entire expression, we first need to figure out the left side, and then we got to figure out the right side. So to figure out the left side, we just like go to the left. We go here, and then we have to figure out its left and its right, starting from the left. So we go to its left, which is just 2. We backtrack. We go to its right, which is a 3, and then we apply the multiply operator to the left and the right, and then this is going to get turned into a 6. So this is going to be a 6. And now we backtrack up here. We know that the left side is a 6, so we got to get the right side. And to get the right side, we just visit it 4. And so we then can form this operation, which is 12. I guess we don't even need the brackets here. Or sorry, not 12, it's 24. So 24. Now the natural production that would produce this would look like this. So you have multiplicative expression would be multiplicative expression times atom, or it could be an atom. So this would be the natural production that would lead to an AST node that looks like this. The problem is that recursive descent can't actually parse this, because we'd have this multiplicative expression function, and this, let me just bring this down here. Our start token is here. Now this wouldn't consume any tokens initially, because we need to first decide whether to parse it as this or as that. And let's say that we decide to parse it as this. Now we have to get the left side by calling this function again. And as you can see, there's like infinite recursion. This is what we call left recursive. That means this non-terminal shows up as the leftmost like element on the right side. But that's okay, because there's a really easy way to get around this limitation. It is, instead of using this production, we're going to use this production instead. Atom, I'm going to put this in quotes because to disambiguate this multiply with this right here. So our production is going to look something like this. And it's very similar to like this params or this like expression list down here in the way that we parse it. Let me actually just put that to the right, and let's pull up the code for parsing expression list. So just like parsing this, we're gonna have like a while loop, or actually I guess we need to parse the first expression first. So I guess first actually let's do the pseudocode. It is going to be Atom. Now we have a while, and so we only continue the while iterations as long as we see an atom, or as long as we see the multiplication operation. While token is multiply. Now, if we see a multiply token, it means the right side has to be an atom. So we just assume multiply, and then we call atom, and then we kind of just overwrite the first with like a binary operator, bin op, which is going to be this. So this first becomes the left-hand side of the next operation, and then this atom right here becomes the right side. We make it even simpler. And this loop is going to keep executing until we get to a token that's not a multiply. So let's actually see a more realistic example. Let's turn this actually into a better example. I'm going to delete all this. So if we had something like this, like A is equal to this, then what would happen is we try to parse this whole thing as an assignment statement. And then eventually, like the assignment statement is going to consume the side. And then it's going to get to here. And so we're going to call, let's call this function multiplicative expression. We're going to call multiplicative expression here. So we parse this as an atom. And then our first is going to just be like 2. So actually, I'm just going to, so first is just going to be 2. Now we consume this, because actually Atom is going to consume and give us back this AST node. We see, okay, there's a multiply here. We go ahead and consume it, and then we overwrite first with the binary operation node. Of course, the operator is multiply. And now this first becomes the left child of this node. Then we're going to obtain the right child, which is the atom. So we call atom, and then atom is going to consume this 3. So we have this right here. And now we see, and then we go back to this, go back to here, and then we evaluate this condition, and we see, okay, there is a multiplication node, so we repeat the entire process. We assume this, and then we have to prepare another binary operation node. And this first, so the first was this, that now becomes the left child of this top binary operation node. And then we consume, so we consume this, and then we're going to call atom, and then atom is going to consume the 4, and so the 4 is going to become right child of this binary operator, operation node, and then we go back to this condition. And because this token right here is not multiply anymore, we will have returned, we will have constructed the AST for the entire expression. So we just like return it, and that's the AST for the entire expression. Now, instead of just supporting the multiply, let's just say that we now need to support the plus, and plus has lower precedence than the multiplicative expression. And also, let me just delete all the stuff here. And the production is just going to look like this: add additive expression, going to be multiplicative expression plus. We don't have to put this in quotes because we have to. But it's going to look something like. Actually, let me move this here. And so like the way to view like an additive expression is, let's just say that we had something like this. So 2 times 3 plus 4 times 5 plus 6 times 7. Another way to view this is just that it is like this. So it's multiplicative expression plus multiplicative expression plus multiplicative expression. So we're going to parse like our first node is going to be whatever multiplicative expression gives us back. And so like we start from here and we start from here, and the multiplicative expression is going to give us the AST node. This, and then like, and then we see, okay, there's a plus, so then we consume that, and then we get the next multiplicative expression by calling the function of this, and that's going to consume this, and then we see another plus, and then like we call multiplicative expression again here, and I guess there's an end file. Actually, let's not even go that complicated, but yeah, so we do this, and then let's just say the next token. So this is a little bit like less formal, or a little bit more ambiguous, but like this, like if we just had the while loop from before, then we could parse the additive expression like this, and if we had another operation that we want to support with even lower precedence, like let's say less than, then we would do something like this: less than expression, the additive expression, and that is, so the AI suggestion is there. This, yeah. So we would just do do this, and if we had another one, if we supported just a bunch of operations that at lower precedence, then we would just have an entire chain of these. We have another entire chain looks like this, and we'll see that in a little bit. But this only applies to operations that get evaluated left to right or left associative, and that's because recursive descent can't parse this. And it's only because recursive descent can't parse left recursive productions. Now, if you had an operator, if you had an operator that was right recursive, so let's say exponentiation, then you could do something like this. So exponentiation expression goes to let's just do this atom or exponentiation expression, and then you have a right leaning AST node. So if you had 2 times 3 times 4, you'd have binary operation, and then you have a 2, and then you have another binary operation, and 3 and 4. This is okay because this is not left recursive, so recursive descent can actually parse this. But we're not going to support exponentiation. We're not going to support any right recursive operations. So we don't really have to worry about this case. But this case is a lot easier to handle than the left recursive case. All right. So at this point, I'm just going to go ahead and create this chain. All right. So here's the expression binary operation chain. We are going to support or and then we have the quality operators, the relational operators, and of course we also have And then we have the multiplicative expressions, multiply and divide and modulo. So these operations are all have the same precedence. So if you see like multiple operations that corresponds to like one line here, that just means have the same precedence. Now let's go ahead and add the binary expression or binary operation node. Where's add it? What do you want to add it? I guess we can add it here. And I think I'm actually gonna call this a binary expression. I'm not gonna call this a binary op, even though we like binary op. But this is how it's gonna look like. You have the left side, you have the right side, and then you have the operator. I think we're gonna be a bit more specific with the operator as well. And I'm just gonna copy paste all of the operations. So that's our binary expression node, and let's go ahead and put it in. Where's the expression union? In this expression union right here. So we haven't added support for unary operations yet, or like calls and like access and all that stuff. We'll add that later. But let's get the parser going, and this part is going to be extremely anal, as you'll see. So we're gonna need to create a function for each of these. For expression, this is gonna return the binary expression. I think I might just get the AI to like generate this, like empty. See if it works. See if it can like figure out. Oh, I guess we can put private here. Okay, I don't want them to. I don't want the AI to implement anything yet, so I might just like do this. If I wasn't recording, I'd probably just like use a like a. I'd probably just use an agent to like make this for me. But here's our left, and then yeah. So we need to check the or. We need to check for or rather. And then in here, we don't do this. Actually, we just consume. And then there's our right side, and left is to have to be that. Let's this as a binary expression. And why did this? All right, we need the location. And we can just return left. And for this and expression, it's basically the exact same loop, except this right here is going to be an and. And then this equality expression is also the exact same loop, except there's two equality operators. There's the double equals and the not equals. So this should be like a double equals and a not equals. This is what I mean by when I said this part is menial. It's just a whole lot of copy paste. Or here. And I guess you have to update this part too. I forgot to update this. And we don't need this location here. Here there's two token types that we might want to eat. And that's that. But we actually need this. So operator. Yeah, then the operator is just the type. Equals or not equals. And this operator should be that. That. This will just be operator. Here, I guess we can do that. Yeah, so I'm just gonna copy paste all of this and modify like. Oh, actually, there's a mistake here, which is you have this and expression. This and expression should actually be the equality expression, because we want to go down, or we want to go up in precedence. And then this AND expression here should also be the relational expression. And then this relational expression, or this AND expression here, should be the additive expression. So where's the relational? So we have all of these. I could put like all these operators into a string set, but I think this. But it's actually less than equal to and greater than equal to. And are we eating the correct tokens? We are eating. So we're eating the correct tokens here. We're eating the correct tokens. We're eating the correct tokens. So we gotta eat the correct tokens here. And cast this. Like, I forgot to put the as. Oh, it's okay. Now copy paste this. Multiplicative expression. Multiplicative. What do we have for multiplicative? What do you have for additive expressions? I mean, just plus and minus. Okay, multiplicative expression. We have the operator, and now we have to change this plus and minus, and now we just have this last one right here, which is going to be an atom. I guess make this an actually, let's just make all of these an expression line. Okay, so plus multiplicative expression is this, or it's this, or multiply, divide, or modulo. F here, and I think I'm just gonna delete or the right side. Okay, so there's a lot of like a code that got repeated that's like almost like similar, or is similar. It's almost the same. Now there is a strategy to like not have all of these functions and instead just collapse all of these into a single one, and it saves a lot of code, and it's called parsing. And this is actually pretty common in a lot of recursive ascent parsers because it just simplifies the code substantially. But I'm not going to talk about it here because it is conceptually like a little bit more challenging than this. So, so yeah, we're just going to ignore the parsing and just have this chain of functions here. Okay, so now we can actually go ahead and do some testing. So let's just, how do you want to do this? I guess we can just do this. 1 plus 2. Let's just try like a really simple expression. I guess we can add 3 as well. Main, right side. So at the top, we have this expression statement, and then the expression is just a binary expression. And the operator is plus, so that's good. We want the plus to be at the top because we want to evaluate the multiply first. And deeper operators get evaluated first. So on the left side of the plus is 1. And then on the right side, you've got the 2, and then you've got the 3 over here. Now, if I put just to test, like just for sanity test, we'll do this. So let's see what the binary expression. So on the left side, let's collapse the left. Let's see if the operator is correct. It's multiply. right? So this time it's multiply because the expression or the brackets tell us that this 1 plus 2 is supposed to have higher precedence. Because that this is a multiply and that this left is a parenthesized expression with this binary expression right here. And then the right side is just this 3. So let's try a more sophisticated expression. And I'm gonna pull out the this just to see like what operators we have. Okay, so I think I'm gonna try like all the operators. Let's do an or. Okay, maybe I'm not gonna try all the operators because that's like a bit of a pain. But let's do true, or I guess true and false. Uh, okay, so the operator is this, and then the left side is just the true, and then the right side is another binary expression, which is the and now, whose left is true and whose right is false. Okay, so this is good. Let's try this. So if we go back here, we see that the equality expression has higher precedence than the and I think I'm gonna put a less than here, 1. Okay, so expression, this should be the operation. So let's collapse the left. Okay, so there's the operation. Now the left should be the less than. Yep, the less than with 1 on the left of that, and then true here. Let's look at the right side now, which the first operator, yeah, so the top level operator is the and the left side is just false. Oh, wait. Oh, sorry, that's the right side. The left side is true. No. No, yeah. The left side is true, right. Left side is true, the operators, and the right side is another expression where the operators, the equality, false on the left, and number literal on the right. Okay, so I'm just gonna test like a bunch of different expressions to see if we get the right AST. And I might get the AI to like generate some of these test cases. Okay, so I've tested with a bunch of very sophisticated expressions, and I'm convinced the parser is correct. Now we're just going to add the finishing touches by adding support for unary operators, as well as calls and property/element access. So let's let's finish our syntax specification, all these empty spaces. So unary expression, and the unary operations or operators that we're going to support is not, or the. I guess we don't have to support the unary plus, but let's just do it anyways. And there's this access or call expression. So this multiplicative expression, or sorry, unary operators have higher precedence than multiplicative operators. Okay, so access or call. Put this on another line. This is access or call, and it's going to be an atom followed by a prop access, element access, or call, and any number of that. Like this is an example of an access or call expression, say like object a5, I don't know, call with maybe like 5 and 6 as arguments. So that's like what this production is going to allow us to parse. It's going to allow us to parse this. So let's add the prop access. And prop access is just going to be a dot. That would be this. This will be access. And then there's element access, which is just an expression inside square brackets. So it would be. Sorry, this is the prop access, and this is the element access. This would be the entire like access or call expression. And of course, we want to evaluate this first. Parse it into node where we can do that. Now lastly, we have the call, and the call is just going to be an expression list. And of course, like the arguments are optional because some functions don't have arguments. The expression list is down here, just like literally a list of expressions. Yeah, so let's work on our parser now. Where is multiplicative expression? So we have to introduce two more. Actually, we have to introduce a bit more than two. Let's introduce a unary expression. Actually, before we do this, let's go ahead and make our AST. So binary expression. We now have unary expression. Base node expression. We have to add the plus operator here. This left, and then here's the right side. But do I want to call this right or do I want to call this operator? I think we can just call this right. Or actually, I think I'm going to call this argument. Now we have the prop access. We have the access or call expressions. So we have the prop access, which I think I'm gonna call this the target, and then this is the property. But the property should actually be just an identifier. Yeah, there's the identifier. Element access. And this one's going to have a target. It's also going to have the index, which and lastly we have the call, which extends the base node callee. I think I'm also going to call this the target. And then we have the arguments. I call it arguments of arg. And all of these, I think I'm going to add a type here called access, which is prop access. And then a type called access or call. Got this wrong. Just access or call. All right. So that's our AST nodes. We have to add it in up below. The expression. This is going to include a unary expression or access or all. All right. Now let's add the functions. So access expression, access all expression, access. Actually, you know what? These like prop access and element access are just really simple, so I'm not going to introduce the prop access. I think I'm going to do everything in here. So because actually we need to add the look aheads unary expression. This. And now the expression, we have to update the expression look ahead because if you check the first token that could appear in an expression, it can be any of these. Either atom look ahead or it's a unary expression look ahead. Yep. All the way down. And this multiplicative expression should now try to construct the left and also the right expression nodes now. So we have a we could do this iteratively or we could do this recursively. I think I'm just going to do this recursively. But I think it's probably a little bit easier. But this token, if his unary look ahead, then we just eat that, and we get the argument, and that's just the node. So let's check this. Argument is a unary expression. Here's the location, which is start of the token and wherever the argument ends. Okay, cool. Now we can just return this access call expression. Private. Gotta make all these private. Okay, so access or call expression, the left it is going to be, I think I'm just gonna call this the I want to call this left. Yeah, okay, let's just call this left. So now we have some cases. I think I'm just gonna do a while true loop here, and we can add a break. So here's the token, and if the token type is a dot, then this means that we need to parse as a access. So we're going to eat the dot, and then the property is going to be just the identifier token. Then we can construct the left side like that. So let's check this. Access target is the left side. That is correct. The property is the identifier. Have the name. We have the location, which is the location of the token right here, and then the location of the entire AST node is this, which I don't think is correct. It should be left. Location.start. Yeah, it should be left dot location start. Now, if the token type is this, let's do an else if here. And we're going to eat the open brackets. We're going to get the index. We're going to eat those brackets. And then we just create the node like this. Element access target is side. Yep. And we have the index, which is the expression. The start is going to be left here, and then right is, it should not be index, it should be this. All right, so access or call, and we now just need to do the call. Eat that, and before we get the expression list, we need to check, or rather, before the arguments, we have to check if the current token that we're on. Okay, so we have the arguments, and check this. So it's a call. We have the target. Why is that? Okay, we can't actually use the term arguments as a variable. JavaScript. The start is the left location start, and then the end. Okay, so that looks good. Now, if it's if the token here isn't any of it's not a dot, or it's not a open square bracket or open circular bracket, then we just break out of it. Yep, that's correct. We just return to left. All right. So let's go ahead and do some testing. Simple print flow program. Okay, expression statement. There's our call. We have the identifier, which is print target. The arguments, we only have one argument. And let's say we don't have any arguments here. Call, identifier, arguments. All right, let's do a more sophisticated change. Or actually, let's do this first. Object dot foo bar. And don't forget the semicolon. Okay, so expression statement. And this is our expression. It's a property access as expect. So the target is going to be this, which is a property access in itself. And the target of that is just going to be this object right here. And the property is going to be the property of the outermost property access is going to be this bar. Okay, so last, I'm going to check element access now. So say 1, 2, 3, colon. Okay, so expression statement, element access, and the targets. Actually, let's just check the index. That's probably the easiest. So the index corresponds to this, which is just 2 plus 3. All right, now let's check the target. The target corresponds to this. We have an element access, and the right side, the index, 2 right here, so that's 2. Target is this thing, which is the another element access, and the target this time is just the array, and then the index is... Okay, so this looks correct. Now I'm gonna test. Actually, let's make a real program. Let's do this in main, because we have at this point our parser is complete, so we could just start like testing like actual programs. Count is equal to 0, while count is less than 10, count is equal to count plus 1, break count, call main here. So function declaration, and I'm just gonna like check a bunch of different cases, and I'll probably run the parser through Gemini to see if there's any errors. All right, so again, I've tested with a bunch of very sophisticated programs, and I'm convinced that the parser is correct. Let's move on to actually implementing the code execution, or the backend. But actually, first we need to discuss the scoping rules of our language. So let me delete all this stuff. We're going to use function scopes, and what that means is that variables will be tied to functions and not to bodies or of loops or if statements. So let's say we had this program right here, or so fn main, and let's say we had this if statement here, and we create a variable inside it, and then we print outside it. We run main. This function is actually going to print 15 because this 15 actually is tied to the main. It's not tied to this block of code. And to resolve variables, we're going to use LEGB. We're going to borrow this concept from Python, and what this stands for is local, enclosing, global, and built-in. So let me kind of demonstrate this with another program. So let's say that let me delete this actually. Let's say we had this variable over here. This would be tied to the global scope. Global scope is just like the scope, like at the top level. It's not tied to any particular function. And then there's built-in, which you can't even see it, but that would be like runtime functions like print. And we'll load that in. We'll talk about how to like load those things in. But let's say we add a function here, outer, and then fn variable here, fn inner. And inside here, let's print the a, and let's call it inner, and let's call outer. So this is actually going to print 5, because when we get to here, we use this rule to figure out like where to find the a. So we look at the local scope. The local scope is just scope tied to the inner function. And we see, okay, so a is not like defined anywhere in here. So then we go to the enclosing scope, which is the scope tied to the outer function. And we see, oh, okay, there's an a here. There's an a here, and it's equal to 5. And so that's the value that we're going to take for this variable. Therefore, we print we print 5. Now, if I removed this, then this is going to print 200, because it's going to look at local, can't find an a. It's going to look at the enclosing, which is the outer, and it can't find the a either. So then it looks at the global scope, and okay, there we have it. There's an a, and the value is 200, so we're going to print 200. Now, this language is also going to support closures. So let's say I did something like this, the init, and let's make another function in here called get. And let's just say we return the init here, and we return the get. And outside here, we do this. Oops, sorry, that's not v1, that's v2. So these two are just going to be like the get functions. If I print v1 and I print v2, this is going to print. This one's going to print 0, and then this one's going to print 10. So we're going to print 0 and 10. So we will have to support closures. Yeah. Every interpreter has memory and a code execution engine that mutates memory as it proceeds. So let's talk about the memory picture first. There's a stack and a heap. And stack frames contain things such as local variables, parameters, and also return address. And there might be like a bunch of other stuff. And the heap stores like values of reference types. Of course, this is a big simplification. Now, in an actual like production grade interpreter, there's a bunch of complexities when it comes to managing memory. Like, for example, like the interpreter needs to request memory from the operating system, or if you're working in even like lower level environment, that you might have to like do some funky business, like do some funky stuff directly with hardware memory. Also, production grade interpreters have to do like garbage collection, and it might have to move memory around when arrays and objects grow too large. And there's like a bunch of other like complexities to go around with that. But since we're high level, we're just going to keep things like really simple. We're not going to do any of that. Instead, we'll just emulate a heap, a stack. Go ahead and do that. Let's create a backend folder, and let's create this memory file. The heap is going to be a class, and it'll have two main methods. It's going to have a set method, and it'll have a get method. And what the set method does is it's going to take in a value. We're going to call this runtime value, and we'll make this type in a little bit. It assigns it an address, and then it stores it. So actually, we have to create a storage, private read-only storage. And also, let's make the pointer. So this is going to map a set of memory addresses, which we'll call pointer, equal to string, which is just a string value. So the set method is going to assign an address with the UID function, and then just store the value at that address. Whoops, ptr is equal to value, and then we ptr. And then this get method is going to take in a pointer. and then it'll return a runtime value if it exists, or if it doesn't, it'll throw an error. Value is equal to this storage pointer, and then we return the value. And of course, if value is equal to undefined, let's this, and we can just throw an error here, and I'm going to call this a segmentation fault error. Invalid pointer. So a segmentation fault, if you're working like in a lower level system, it's basically like where you try to access like out of bounds memory or like some invalid like area in memory. So in this case, if we have we're trying to get something at an address or at a pointer position that like doesn't exist, then we have a segmentation fault. So let's go ahead and make the runtime values, and I'm going to pull out the syntax spec here because the values are going to have to correspond with primitives and also arrays and objects. And we also have to store the functions values because we're going to treat functions and we're going to store those. But basically, we're going to store everything in the heap in like an actual like production grade interpreter. Like some things go into the stack, but we so what values we have? I guess these are all. Let's make the primitive values. So these are all it is. So there's a null value, and we'll just type it as null. And then there's the boolean boolean value. I'm just gonna boolean and value. I guess we'll just follow the AI here. Excuse me. And these are gonna form our primitive value. Is that so? I guess I can close this right now, and we have the runtime value. Now the array value. Let's go ahead and add the reference type values, which is the array. And this is just going to be an array, but the elements it's going to contain the elements are going to be a list of points because this is a reference type. And then we have the object value, and we do have do you want to call it pairs? I guess we'll call it properties. We won't call it pairs. Will be record of names and also points. All right, so last thing that we have to support, last value that we have to support are the function values. And there's going to be two types. There's going to be like built-in, or rather, there's going to be functions that are obtained from function declarations of the AST node, and then there's going to be built-in functions. Built-in functions are kind of like your prints, and then like let's say length, we might add like a length function to like get the size. Let's do the built-in function first. And this is going to be implemented not in like the code of the language, but it's going to be implemented. And the implementation, we're going to have args, which is just a list, and this is going to return a pointer. So if your function, sorry, in this language, like if you have a function like this, and let's say we do like a is equal to 15, and then we do a bunch of other computation, but there isn't a return statement anywhere here. Well, we're going to return null, but if there is a return statement, then we're going to return just whatever the value. So if we return like a here, we're going to return 15. If there's no expression in the return statement, then that means it's null. So for built-in functions like print hello, this is actually going to return null. So if I do something like this and I print, then this part is going to print. That's why like we have to return a pointer here. All right, so now we also have the like regular functions, and this is going to correspond to an AST node, or rather the function declaration AST node. But since we're going to support closures, we also need to track what is called a lexical environment, and I'll explain this in a little bit. But let's just get these values added to the runtime value. Okay, so let's go ahead. Actually, we need to export this heap. And now let's talk about the lexical environment. This is where we're going to store local variables. We do need a name and class environment. And every lexical environment has a parent. So you can think of a lexical environment as just like an instantiation of a scope. And this is also going to have two main methods. It's going to have the set, which is if we want to add a variable, then or rather we want to initialize a variable, then we just call the set method. Just like that. And I guess we could also return. I'm thinking, do we want to return the pointer? Because the thing is, actually, let's just do it. Let's just do that. Let's not do any of that. Let's just implement the get method. This is gonna give us the pointer for a variable provided it exists. So this is where we're going to actually respect the LEGB rule set for resolving variables, and that is where we're gonna try to find the pointer of we're gonna try to find the variable in the current environment. If we found it, then we can just return the pointer. But otherwise, we have to look in the parent. So we need to check if the parent exists. And every lexical environment is going to have a parent except the built-in. The built-in is the only one that's not that like doesn't have anything above it. So we don't have to return this on. So if a parent, then we just try to get the variable in the parent, and so on. So why do we need a lexical environment if we're going to implement functions? Well, let's just say that we didn't have the lexical environment, and let's say that we have a program like this. So we and take an init, and then we have a fn.get, and this get is going to return the init. Then we return get, and then let's just call v on 0. And so what would happen is that if we stored all of the local variable pointers on the stack, then we would execute this, because we're going to call v down here. We're going to execute this, and then that stack frame is going to have the init. Like if we have like our stack, it's going to like have something like this, and then here there's going to be a init to this. But once we finish executing this frame, or rather this this call, then this frame actually gets popped, so that we lose this init variable. And then down here, when we call g, well, g is just this function right here, and this function needs a reference to the init. But because we popped it from the stack, we don't have that reference anymore. So we can't actually we don't really know what this is. So the solution is to just create a lexical environment and then store it with the parent. So when we create this get inside the heap, then we store alongside it the lexical environment of its parent, which is the lexical environment that corresponds with the call of v. And so when we call g down here, we'll create another lexical environment and then set this one as the parent. And because that one has init, we can actually get the init by traversing up through here. All right, there's one more memory component that we have to implement, and that's the call stack. So let's implement that. And the call stack is only going to have a push, a pop, and a peek for its main methods. And we also have to create a call frame, or you have to create the type of each frame. Now, every frame is definitely going to have a lexical environment. Sorry, not local environment, lexical environment. And we can also give it an identifier, ID, fn. We also need the name, the name of the function that this frame corresponds to, and I guess we also need to store the node that we're currently paused at in this frame, because in the debugger visualizer, we're gonna have to highlight that piece of code when the user clicks on the frame. So we're gonna store the AST node that we're paused on. I need to export AST export. Okay, and let me just check that this is complete. So statement, expression. Yeah, this looks fine. Memory. So that's gonna be our frame. And let's go and actually create the stack. Or I guess we'll just call it frame. That. So push is gonna take as input. It'll take the function name. It'll take the AST node that we start at. So this should be a block. And then it'll take the lexical environment. The code execution engine is going to be responsible for creating these lexical environments, and then we just push the frame onto here. So on one line, and then pop is well, we just do that, and peak, we just need to get the top frame. Just going to turn a frame. And so yeah, that's pretty much it. This is the call stack. I guess for all of these classes, we do also need the all method. So for the heap, we need to return the entire storage, because our debugger needs to generate like a heap snapshot, and it also needs to generate a call stack snapshot. And to generate the call stack snapshot, it also needs all the variables in local environment that corresponds to the frame. So I have a all right here, and this is just going to return the variables, the type, and there's an all here, and it just returns the entire frame, or returns all the frames. I mean, and yeah, this is all we're gonna need for managing memory. Okay, now we're at the most important part of the interpreter, which is the execution engine. And this is going to walk the AST. But in a standard AST walking interpreter, you'd usually have like a recursive function down here called like exec. And this is going to take in a node. And it might take in some context as well. And this context is going to contain like the heap, the stack. I'm going to write some pseudocode here. And maybe some other like stuff. But you're gonna have like, you usually have like this giant switch statement that like just like does some things depending on like which node it's at. It might like call like recursively call exec to execute like the nodes below, and then every time it executes like one of these nodes, it'll just like update the context. But for us, we unfortunately can't really do this. You know, we really want to do this because this is like the simplest way to implement an interpreter. But we can't actually do this because we need to support breakpoints, and therefore we need to like pause program execution, and that's not easy to do with the recursive function. So what we will build is we're going to build a state machine, and I'm gonna put it in a file called run. So here's run. And this state machine, I think I'm going to call it the executor. And it'll have two main methods. It's going to have the advance. Actually, it'll only have one main method, which is the advance. And this is going to run the program up until it either finishes or until we arrive at a breakpoint, at which case it's going to return the execution state. So we'll also need like the state. Like we'll also need the state method function, and I guess we can just throw a new error here. Call it to do, because we have to implement this. The state is going to contain the heap snapshot. It's going to contain the stack snapshot, and it'll contain some others that we'll implement later. Now this executor, so there's a decision that we have to make. Do we want to initialize like like the built-in environment and the initial like call stack, and like do we want to initialize like the program execution in the executor, or do you want to do it externally? I think I'm going to do it externally. So this constructor is going to take as input like a configuration, which is going to contain the heap, and it's also going to contain, I guess it definitely has to contain the program. That's for sure, and this is but it definitely has to contain the program. It contains the heap, it contains the call stack, and I think I'm also going to have this printed array to store like the outputs when we call the print function. Yeah, and then here are the members, so private read-only heap. Pull these in. Let's just do that for now. So this dot heap. I guess we also need printed. We gotta load in the printed. Yep. There we go. So actually, in addition to advanced, we also need the ability to add breakpoints. And every breakpoint is just going to correspond to an AST node ID. Did I have this exported in? Yeah, I don't think I have it here. No, I don't have it here. Let's go make this variable. This is just like more descriptive than a string. I really like to do stuff like this. Is what ID back is spelled that, and we also have declare breakpoints. Yeah, so let's also track the breakpoints in a set. Okay. So let's just talk briefly about how this advanced function is going to work. We'll go into like more detail when we actually implement it. So because we can't traverse the tree recursively, we have to simulate a recursive stack. So we actually need an execution stack above. And for now, I'm just gonna type it as any. I'm just gonna put to do here. But the way advanced is gonna work is that we're gonna have this while loop, and so the program is running if this execution stack length is greater than 0, and then this execution stack, exec stack, is going to be initialized with just the program. Program is a block of code. Now at every step, it's gonna look at the current like AST node that we're traversing, and then it's gonna do a little bit of execution. So let's just say that we had a program like say this print a b. So like maybe like in the first iteration, like we would let's put that here. We would we would run the block, but then we would run this function call right here. So this would be like a call, and I'm just gonna like make like a note here, print a. And then in the next iteration, the top of the stack, I guess the whatever is on the top of the stack is going to be the current node that we're visiting. So we visit this call, and then we need to actually like call the print function, and there's a lot of details that we'll talk about. But once like this call is done, then this is gonna pop, and then the next iteration is going to run, and then we're back at block. So alongside each AST node, we also have to track some state. So in the block, like we have to track, like for example, the index of the next statement to run. Because if we didn't track this, then what would happen is that so let's just go back to this call right here. So in one iteration, the top of the stack is the call, and then we run it, and then we pop this, and then we move on to the next iteration. The problem is we come back to the block, and because we don't have this, we don't really know what the next statement to run is. So it could either be this A, it could either be this B. But we do need to track some like state with each block. And part of the challenge here is to figure out like what state we need to track, and also the logic for actually performing the execution. So yeah. But if we're to just like build a really like high level function right now, and we can abstract away like all the execution logic, then it's gonna look something like this. While this exec stack length is greater than 0, then we have the current, which is this exec stack, and we don't want to pop it right now. Get it? And then we just execute the current. We'll add this exec function as well. So we pass in the current node, or not node. We pass in the current state, and then we'll just have to pass in like the heap and the printed, and exec stack. I guess we don't need to pass this in, but we do need to print. We do need to pass in these heap things. So this exec is going to be responsible for mutating the state of the heap and also the state of the stack and the exec stack as well. Now, if we ever get to a breakpoint, so let's say if this breakpoint has node, and I guess we need the current. Actually, we don't need the current. Whoops. Let's not talk about that right now. But if we ever get to a breakpoint, then we just return the state, and then the next time advance gets called, it'll just like continue from where we left off based on what the top of this execution stack is. So at this point, we could talk about the stuff that goes into the execution stack. So let's go ahead and do that. Okay, so we're gonna create a context.txt, and we're gonna call context.ts rather, and we're gonna call every element that goes into the exec stack context. So every context is actually a state object that corresponds with. And we're going to start very small. We'll only like initially we'll only be able to run programs like this. 3.45, like basically programs are just kind of listing out primitives. But let me actually pull out the AST here, and let's I guess so. Okay, so we're gonna support block and we're gonna support primitives. So let's make a block context. Block text to the type block. And for the block context, we do need to track the node of type block. And we said earlier that we have to track the position, or rather the index of the next statement to execute, and we're going to call that the program counter. We could also call this index, but I think I'm going to call it the program counter. And then we're going to have a primitive interface, primitive context, type primitive, and there we go. And we don't need this. See here, primitive. Okay, so now let's think about it. What does it mean to like execute a primitive? It just means put the literal in the heap and bubble up the pointer. So if it is a literal, or if it's an identifier, then just get the pointer to the value and then bubble it up. So we do need a place to store that pointer, and so we're going to introduce this thing called an accumulator, private only accumulator, and for now it's just going to contain the pointer. We'll initialize it down here, and we could set it to the number 0, but I think we're going to set it to null instead. or the pointer to some random null value instead. If we look at this program, which we want to get, which we want to execute, the AST is going to be a block at the top, and then it's going to be an expression statement, and then it's going to be a string literal, and it's going to be an expression statement again, and it's going to be a number literal. Okay, so we also need the context for the expression statement, which the node is the expression statement. Now, what does it mean to execute an expression statement? It just means execute the expression. That doesn't really get more complicated than that. And for now, our expressions can only be like primitives, so it just means like go and execute the primitive. So let's actually create this exec ts where we're going to put this function right here. Actually, let's export the context types that we have so far. So here's the context type. Let's play on different lines. So export function exec, and this is going to take the context text, and I think we're going to call this thing state. Yeah, let's call this thing state. Also, we have to pass in the accumulator. Interface state heap. We have to pass in the heap. Pass in the call stack. Pass in the exec stack. That's the context, and then the accumulator. I guess it's just this. Or maybe we can even put the type here. Yeah, actually, let's just do that. I guess we also have to initialize the exec stack because the exec stack in the beginning needs to contain the context, needs to contain the context of the entire program. So over here, I think we're going to create this function called init context, and it's going to take an AST node, and it's going to context. Where's the block? I don't have block here. That's kind of strange. Okay, let's add a block here then. Whoa. So for this, type this block, the node, that, and then the program counter is going to start at 0. And where is the primitives? So these are the primitives. Put them all up here. And we can just return this. And the other one is the expression statement. Our node. And I think we're just gonna throw a new error here. Well, actually, let's throw in a default block. All right. Do this. Actually, we need we need 2 phases here. We need an if phase and a done. I'm just gonna put in some code right now, explain like I'll like walk through this executing. Just kind of like demystify this, but I think like we do need to front load some of this stuff. State Like, why is this? Oh, okay, and switch. Okay, whoops. ptx.type. Or actually, let's make a function here called like block. Block context. We need to export all this stuff. Okay, so when we execute the block, we need to check the program counter first if we finish executing it. So it's x.node.statements. And if this happened, then we can just pop from the exec stack because we're done executing the block. That's what it means. Return. Otherwise, we need to execute the next. This is a squiggly line. Okay, so if yeah, so otherwise there are statements that we have to execute. So we have to get the current statement that we're going to execute, and we increment the program counter, and then we just push context of the next program to execute. Maybe we should call this next. Now, when we execute primitive, there's two parts. There's a phase init. So if the phase is init, it means that this just got pushed onto the stack, and we haven't called exec on it yet. So there's actually two cases here. Actually, there's a couple of cases here. First, we have to switch over the node type because we have to figure out like how to write it to the heap. That there's this, and in the case of identifier, we don't actually write it to the heap. But if it's a null literal, then we can just set the accumulator to be the pointer. You just do this state dot set type null, and we break val is state dot heap dot set. So this time it's a Boolean literal. It'll the type B. It's float value. Whoops, sorry. This is Boolean. This is the value. Type a string, context at null.value, break, val is state.heap.set. Number literal Boolean string, and then we come to the last case, which is the identifier. So we just have to figure out what the pointer is, and we can get that from the what should we call it? The lexical environment, which is stored in the call stack. And if we don't, if this pointer doesn't exist, it means like we're trying to access a variable that doesn't exist. Like if we do something like this, and then we never like declare this a anywhere, then we're gonna be throwing an error here. And we'll call this a reference error. Otherwise, like this is gonna point to the value stored in this variable. So we can just bubble it up in the accumulator. We break over here. I guess we can return. But actually we need to set the phase to completed before we return. Because, or I guess we called it done. We gotta set the phase to done just to signal that we have like stored like these values into the heap and that we bubbled it up. And then if our phase is done, then we just pop the exec stack, and then we return. If we don't really need this return, but I'll just keep it anyways. So that's how you execute a primitive. And then executing the expression statement is kind of like really similar because the expression statement also has the expression statement also has like two phases. It just has the init, so the phase is init, and we can just kind of set the phase to done. But actually, before we set the phase to done, we're going to push the context of the expression to the execution stack at ctx, and then it's done. Otherwise, if it's already done, then there's nothing left to do. So we can just pop it off the execution stack and return. Again, we don't need this return, but I'm just gonna put it like here. Yeah. Now we have the executors for each of these. Exec block. Exec statement state. Okay, so I think what happened here. All right, we need a phase. All right, we are almost ready to execute this code. There's actually a lot that goes into even getting like the first execution going, but the only thing we need now is to prepare the executor. So what that means is to create the initial call stack, to create the initial actually we just need to create the initial call stack with the built-in environment and also the global environment. What's an environment? I mean lexical environments. So we'll have a function down here. We need to export it because eventually we're going to be calling it on the front end. And I think, what do you want to call this? I think let's just call it executor. And this is just going to take in the program and it's going to return executor. So let's initialize printed. We do have printed here, and yeah, we do have print. Although we kind of initialized it here. I'm trying to think. Do we want to initialize? Actually, let's just initialize it down here because eventually we're going to load in some. We're going to load in the built-in print function, and it's going to need to write stuff to printed. So let's keep, and then let's create the built-in environment, which doesn't have anything in it right now. The global environment, which has as its parent the built-in env, and now the call stack. So new call stack. Call stack. And then for the first frame, it's just the global. I guess so. So we have to push a function name. I guess we don't have to push a name for the function if it's the global frame, and then the node is just the program itself and the global end. And then we can return a new executor. Here, program, passing the heap, passing the printed, passing the call stack. Not printed. Oh, right, we have to give it this type. What's the type? All right, so we have the executor function. Let's go to main.ts and let's program in here. We don't really need node, so we have the AST here. Whoops, not parser, parser.parse. Let's do this executor AST, or I guess we could call this program even. Oh, we can't call that program, we'll call it AST, or I guess we can just parser.parse. And then we just do exec.advance. And I think I'm just gonna run this code. Whoops, I'm gonna run it in a debugger so we can see like how this code like works in a little bit, but I'm gonna run it first outside the debugger just to see that like there's no errors or anything. There's a bunch of errors, cannot find module context. Right. Put .ts here. If you're running TypeScript directly, then you have to put like these .ts extensions. Otherwise, I'm not gonna be able to find the file. Cannot find module memory in here. There should be a type here, or just a pointer. Or an AST node. These should also be typed. Okay, cool. So that's, we now got this to not error. Let's go ahead and run this in a debugger and we get to see how the executor works. I'm gonna put a breakpoint right here, right before we perform the execution. And we haven't really done anything about breakpoints yet, but let's just see that this, see how this piece of code executes. So why don't I put the main over here just for just to reference code and do that. So here's the debugger. Whoops, I have that from before. Let's test the debugger again. That's the parsing. Okay, so we're about to do the execution. And I'm going to expand this. And we can see like here's the current context with the program counter set to 0. Let's see if I can. Okay, so here's the call stack. And here's the frames. This is just a global frame right now. Let's go environment. But I'm also going to open up the exec stack, also the heap. I'll collapse these. So first we're at block, and we're just preparing execute this. So we're gonna push the context of this expression statement onto the where's the exec stack? Onto the exec stack next, and you'll see that when I click. Right, so you see that this is the expression statement, which is what's currently like at the top of the stack, and the phase is currently in it. And then if I run this again, then here's the primitive, and here's the string literal. So we're currently over here, and in the heap, all we have is null, and that's the initializer for the accumulator. But we should be able to see the string literal if I click next. So here's the string literal with value hello, and then at the top of the stack, At the top of the execution stack, you have the primitive. So we expanded this a little bit more. And this is done. In the next iteration, this primitive is going to be popped. Seed. Yep, it's popped, and now we're back to this expression statement, and this expression statement is now done. So in the next iteration, it will be popped. And now we're back to the block, and so the next statement that executes will be this one. So the process kind of repeats. So if I continue, then this current is going to be the expression statement, the phase is init. Now it's going to be primitive with the phase init. And in the heap below, we only have the string, we only have the null, but we're going to see the number literal soon. Okay, so here's the number literal. And it's 1, 2, 3, 4, 5. There's 1, 2, 3, 4, 5. Now the primitive is done, so we pop it. The expression statement is done, so we pop it. And the block now has program counter set to 2, but this is out of bounds, so this block is going to get popped, and our program is done running. So we are simulating the recursive stack with this code, and this context is just going to guide us. It is just going to like provide us with the states to be able to properly traverse the AST iteratively. So right now, so like the next like step is just to go and implement the context execution for each of these nodes. And I think I guess you could like just do it all in one go, but I wouldn't recommend it. So I think what I'm going to do is, where's my access? What's my call? Yeah, so I'm going to implement the context for this call node first, just so that we can start like printing stuff. And I guess like over here, I also need to like load in the print function in the built-in M. So let's do that. All right, let's making the call context. Call context. Type call node call. And now let's think about. Oops. Oh wait, did I export this? No, I didn't export. I gotta export this. Might as well export these two as well, because eventually we're gonna have context for each of these. What is call? Also delete that. Now let's think about the phases for a second. So first we have to figure out what the target is, but actually we need the init phase, and then the first like computational step is we have to figure out what the target is. So once we figure out what the target is, then the phase should be transitioned to target computed. So if we're in the init phase, then we should be computing the target computed. So actually, let's draw this out a little bit. So let's just say this is the exec stack, and there's a bunch of stuff here. First, it's call. We push the call onto the exec stack, and then the phase is going to initialize as init. Or I guess I'm just going to call it init. So if like the phase is init, then we have to exec the target. So we have to exit this right here. Exit. Let's just call it call.target. And that's going to put in the accumulator. I guess the accumulator right now doesn't have anything, but once we execute this, then we should have the pointer to the target in the accumulator. So we need to set the phase equal to the target computed. Okay, so we do that, and then here we'll probably like have an expression store, and then we do some like other stuff, computation like wise, and then eventually the expression gets popped, and also this call should be target compute. But at this point, like the target is computed, and this accumulator should be a pointer to the function location. So if the target is computed, then we have to go and compute the arguments. But when we compute the arguments, the arguments are going to overwrite the accumulator. So we have to store this pointer to the function location inside the context object itself. So let's just call this target, and it's optional because like when the phase is init, then the target has not been computed yet. But when the phase is target computed, we would expect this to be non-optional. So we would set the target context targets, all the target, to equal to be whatever's in the accumulator. Okay, so we need a phase to represent the arguments that have been computed. So I think I'm going to call this arg computed. And we also need to track all the arguments in the context as well, because there could be many arguments. Yeah, there could be many arguments, and we can only store one value in the accumulator. So the phase is going to be equal to the arg computed, right? And then we're gonna compute the first arg. I guess here like there's a bit of a switch here, which is that if there's no arguments, then we can just that if there's no arguments, we don't have to compute any of the arguments. So we could actually just like get ready to actually call the function. So we need another phase here called already. It would be like phase.callReady. Phase is equal to callReady. And I think I'm just gonna remove this to be like. Actually, let's not do execute target x target. Right, but if there are arguments, then we have to compute the first argument. So to compute the first argument, we have to push the first argument context to the exec stack. And then we have to set the phase to arg computed. And so like we're gonna have like an expression here. And we're gonna have a bunch of other stuff, and then eventually this expression is gonna finish executing, and then this pointer, this accumulator is gonna have a pointer to the first arg. So if arg or if it's arg computed, then we have to put the whatever's in the accumulator into args. And at this point, like there's two cases. Either we finished computing the args, or we haven't. There's still args left to compute. And we can easily tell that by comparing the length of this args with the length of this. So if the length of this is less than this after we put the accumulator into args, it means there's still arguments left to compute. So let's say that. So if args is less than, so if this args right here is less than arguments in length, then we have to push the next argument ctx onto the exec stack. But otherwise we just transition to already. Yeah, we just transition to call ready because then we have all of the arguments in here, and then we're just ready to like actually call the function. Now if we're at call ready, then we have to like actually make the call by pushing. So we would push, or I guess we would initialize the next stack frame, and this should be the next call stack frame. So we would initialize the next call stack frame, and then we would push the. So we have the target pointer, and this is going to be a function in the heap. Push the fn's body context onto the heap. Okay, so we would do that, and so like the next the next thing that goes onto this exec stack is just going to be the function bodies, or the function that we call as body. And so this function is going to execute, and so on. And I guess we also we need one more phase, which is done. We have, phase is equal to done. So this body is going to execute, and it's going to execute, and eventually it's going to pop. And for now, let's not worry too much about the return value. Actually, let's see. Do we want to? Actually, I think we do have to worry about the return value, but let's just think through the case where this phase is done. So if the phase is done, then that means we finish executing. Now we would expect this accumulator to have the return value. So this val is going to be the return value, and if there's no like explicit return statement, then this val is going to be null. And if there is an explicit return statement, then like it should be here. Whoops, it should be here. So I think we actually need a way to figure out. So like we don't actually like clear. Wait, where's my accumulator? We don't actually clear the accumulator whenever we use whenever we consume the whenever we consume its value. I think I'm just going to add a flag here called isReturn. Set this equal to false. So that's gonna mark whether this whether this value right here is a return value or not. And I think this value is also going to be important inside exec, inside this function right here, because like if we return something or we're executing a function, so let's say like this, we have print like after, but we actually return 5. We don't want to execute this, and so this is return is going to tell us to skip like everything down here, and so we're only going to handle the is return when we're executing a call, because like when is return is true, then that means the that's basically the argument. That's basically the value that a call resolves into. So if it's done, then and so like once the call is over, we need to set this flag equal to false, and then we just pop. We just pop from the exec stack. So let's actually fix this. Let's fix this type issue. That is return here. Boolean. And I guess if we do it this way, it means that we could actually put a return statement in the global scope. And then if we put something like down here, this would not actually execute. We would just like halt the program execution to do that. So inside exec, we check, okay, if state.accumulator.isReturn. But actually, we can't just do this for every single context, because in the call context, we have to handle the return. So if it's return and the context.type is not equal to call, put this in the union here. Then we can simply return. We can just skip the execution, because yeah, we can just skip the execution. But actually, I think we have to do a little bit more than skip the execution, because not only is it not executing, we need to actually pop it from the exec stack. Stack.pop, and we're always going to assume that this context object is at the top of the exec stack. This context object right here is at the top of the exec stack. Yeah, although I guess we could like remove this, but I'm just gonna keep it here since I already have it. All right. So that's kind of how this call context is going to work. Let me think. Am I missing something here? You always have to think like really carefully about like how these states like transition, because it can get a little bit tricky. Oh, actually, we are missing something. We are missing something because like if we're in done, there is a case where the function didn't have a return value. So if like our function looks like this, and then we just did something like this, like 5, and then we don't have like a return value, then what's going to happen is that in the accumulator is going to have like a value that points to 5, and that is returned as false. So if is returned as false, it means like we haven't encountered any like return statements, and therefore we have to just set the we have to set this value to null. So like if is return is false, then we need to set the value in accumulator to not to false, to null. To null. Right. And then we pop it. Yeah, exactly. So I think that works. Okay, so let's put this in code. This call. And should be call context. Context. Let me open this up a little bit. So call context and state is state. All right, so turn this into code. So if the context.phase is init, then we transition tx.phase is target computed. Then state.exit stack, push init context, target, return. I guess in init context, also this call right here, which we haven't like initialized the context of yet. Whoops. So let's initialize the context of this call. So type is call, and then the node phase is. Why is this? We'll worry about that in a little bit, right? Because we gotta bring this up top. And the phase is init, and the args is and targets, we don't have to put anything in there because we haven't computed the target yet. All right, so let's implement the call now. So if target is computed, then we have to put the accumulator into the context target, and then we have to decide whether the call is ready or we have to compute the args. If x node arguments, yeah, it's arguments. If the length of the arguments on the node is greater than 0, then it means we need to start computing arguments. Then we have to push we have to push the context of the first argument onto the exit stack. Otherwise, we just say it's call ready, and then we return. Oops. And then the next phase to handle is arg computed. So if arg computed, we got to put the whatever's in the accumulator into the args. Yep. So ctx.args, I'll push the accumulator in there, and then we have to make a decision. So if the context, so if this args length less than context node arguments length, means we still have some args left to compute. So ctx.phase. So we just do this. State.execstack push ctx. And we're using ctx.args.length to be the next argument that we have to compute. So like, for example, let's just say that we have 3. Suppose we have 3 args. So like maybe like here's the or I should say, yeah, let me see this for a second. Right. So let's say we have 3 args in the call. But we've only computed 2 args so far. Now this is gonna have index 2. This is remaining. I guess we call it all. This could be computed. Then this right here is gonna have index 2. And then the length of this is gonna be length 2. So the length is gonna match the index of the next argument to compute. So this right here is correct. But if we've computed all the args, then these two have the same length. So we just transition to call ready because we are ready to make the call. And I guess we can return here. Whoops. Right here. Now this is the meat. The next phase is going to be the meat of this, which is actually to make the call. So we have 2 cases. So let's just actually get the function value first. Target. And target at this point must be computed because we set it over here. So there's always the case where the function value is not actually built in. Actually, I'm going to do this. So if function.type is equal to a built-in function, then the way we handle this case is a little bit different than if it was like a regular function. So let's another if statement or if block for if the function value is not a built-in function but a regular function. And then there's the other case, which is that we're trying to call something that's not a function. And we can just throw an error. We could say like target is not a function or something. And I guess we could type here. And then down below we need a return. So let's go and fill, which one do we want to fill out first? I think we're just going to do the built-in function first. So I think this is like fairly straightforward because in the built-in function, we already have the implementation and we just have to pass in the args. So, and I guess, let's see. So the implementation returns a pointer, and this pointer is going to be the return value. Going to be the return value, right? And we don't have to like modify like is return or anything like that. So we can just do this. Value.impl args. I'm gonna call the implementation with the args that we have computed. And I guess we can just pop it at this point. We don't actually have to transition it. Done, although we could. But we're just gonna pop this because we're done executing the call. Now in this case, we need to create a lexical environment first. Lexical environment. And it's going to have a parent because in the function type, we track the parent environment. So that's going to be, whoops, that's going to be the parent. And now inside the parent environment, we have to load in, we have to match the parameters with the arguments left to right. So that param stuff for each. And then we also need the index here. We need new m.set. let's see. What type do we have? Okay, so we have name. Let's just, yep, so the identifier name, ctx.args I. Now there is a case where we have less arguments than we have parameters. So let's say like this. Then main, I guess, ABC. And then we call main with just 1. So that means this call expression doesn't assign anything to B and C. So if that happens, then we're gonna default B and C to null. Kind of like how JavaScript defaults it to undefined, but we're gonna default it to null. So ctx args, and again, this is JavaScript, so we don't have to worry about this being out of bounds. But if it's undefined, then we're gonna do this. So this is the null coalesce operator. If this is undefined, then we take this value. And that's going to load in the arguments for us. Now we just have to push the state onto the call, or we have to push the frame onto the call stack. There's fn value dot node dot name. It's going to give us the function name. The first argument is this. I made this. I made this an identifier. I guess I didn't make that an identifier. But that's okay. We'll just dot name. And value dot node dot body, because this is the AST node that we're going to be starting at the stack. And of course we need the environment. That's gonna push the call. That's gonna push the frame onto the call stack. And we now need to push the context for the body onto the execution stack. That's it. That's how we make the call. Then we have to handle the call finishing. So if context phase reaches done, it means that we have executed a regular function, not the built-in, because for the built-in function we just pop immediately and call ready after calling it directly. So in done, is return. Oh, I guess we forgot to. So this is pop exec stack, but we also have to pop the call stack. But actually, let's pop the call stack first, so we don't forget. Stack.pop. And so if is return, so if is return state got accumulator. Actually, let's just do it this way. So if is return is true, then that means we've encountered a return statement, and whatever's in the accumulator is whatever is in the accumulator is the value of the return statement. And if this thing is false, then we have to set the accumulator to null. Set type is null. All right. And the last thing we have to do here is we have to pop the execution stack. State.execstack.pop. And that's, I believe this is it for the executing calls. So let's go back to run and let's load in the print function. We also have to implement this. But actually, I think for now, I'm just going to return printed. Or this stuff printed. Here we return the state. I guess we have to return this. After the finish is done or after the function is finished executing. So how do we want to load in the print function? We could do this. So we have to put it into the built-in environment. And so built-in environment. Actually, let's do this. Print pointer. And so we heap.set. It is built-in. The implementation is you have a bunch of args, pointer. I think I'm just gonna do I'm gonna do this. So we have to get the string, we have to get the printed form of each arg. And that's we have to get the printed form of each argument. And we're gonna put that into strings. And then we're just going to we're just gonna string join this with actually with nothing. And then we're going to return heap.set type null, because the print function is always going to return null. So how do we put this into strings? Let's have a look at our types. We may have to traverse the types. But for now, I think I'm going to do something quick and dirty. Which is this. Arg pointer of args. We are going to push based on stringify. The value heap.get arg pointer. So this is gonna print like this entire thing. This is not ideal. We'll come back to this. Let me make a note. Say to do. Come back. This. But at least we'll get to like print something. Yeah. Okay. So now we have the built-in function. We just got to put it into the global environment. So global env. Set print pointer. Okay, print. Okay, so let's go ahead and call, go ahead and run this in main. Let's print this. And let's print that. And let's print this. Whoops, I did not mean to attach a debugger here. Although I may have to attach one because it looks like we have a bit of an infinite loop going. Why do we have an infinite loop? All right, so we're here. Let me expand the exec stack. So here's node, or rather, here's the block, and program counter is 1. Expressions. We have call. Yep. So init. Whoa, call is still init. Kind of interesting. Oh. All right, we didn't do this exec call. We didn't actually execute the call. So let's go back here and run this. Okay, so now we actually printed something. All right. Okay, now we actually printed something here. So that was the issue. I think I'm gonna add breakpoints. This point, we'll add breakpoints. first, and then we're gonna come back and actually get like better prints here. So how do you want to add a breakpoint? Well, the thing is, if I put, let me delete this. If I, let's say, put a breakpoint here, I only want a breakpoint on this statement once. But the problem is that the context for this could appear multiple times. It could appear multiple times in this loop, or rather, it could appear in multiple iterations of this loop. And so if like breakpoint.has, so if we just like try to breakpoint stuff like this, then we're never going to actually finish executing the function. So what we have to do is for each of these context objects, we need to like have a flag, like stating whether it's been breakpointed before. Okay, so I'm going to call this context base. I have it is breakpointed flag, boolean, and this is just gonna, I'm just gonna make everything extend this. Okay, so now what we can do is we could just check. So breakpoint that has the node, and it's not the case that this hasn't breakpointed before. Then we just set this breakpointed to true, and then we simply return the state. So let's go ahead and try the actually, instead of calling it as breakpoint, I'm just going to call it breakpointed. Slightly less verbose. And what happened here? Oh, right. So breakpointed false. You know, we could also make this optional. I think I'm just going to make this optional, so I don't have to handle this part right here. Now setting breakpoints is going to be a little bit annoying manually because we do need the AST node ID, so we like figure that out. Wait, what happened here? Okay, so we were trying to parse it twice. So let's actually not parse it twice. And just stringify the AST. Here we just that's now we have to like manually find the ID of the print statement. I'm gonna put a breakpoint on this. I'm also gonna put a breakpoint on that. So let's see, and these identifiers are deterministically computed. So every time we run this, the identifiers are gonna be the same. So call. I'm gonna put it on this expression same. So ID is 3. Exec.add breakpoint 3. Exec.add breakpoint and words 7. All right, so let's run this. So the first time it runs, it should print nothing. Yeah, so it should print nothing. Let me just actually print this. Click dot. It's console.log. And then the second time it prints, it's gonna print this hello, or I guess it's gonna print the runtime value for hello. So we haven't fixed up our print implementation yet. And then this one's gonna print 123.45. But actually, let me just look at the code again. This breakpointed. I think there is another thing that we may have to do, which is down in printed. We probably want to flush printed. So, yeah, so we probably want to flush printed every time we return the state. Const printed is equal to printed. Length is equal to 0, and this just deletes everything in it, pops everything. Okay. So let's run this. Actually, let's just do this. Okay, so there's hello. And let's move on here. And there's 1, 2, 3, 0.45. So our breakpoints are now working. And I'm going to okay, so I could fix this later, or I could fix this now. I think I'm just going to fix this now. So we need a dedicated function to actually like construct the string for a given runtime value, and I'm gonna make a built-in file, and we'll keep it in there. So we're gonna have this print any, and taking the heap is also gonna take in a runtime value. Did I export runtime value in memory? Okay, I gotta export all of these. So export runtime value and export primitive value. Whoops. Or export. I guess if I export primitive value, I probably don't need to export like this stuff, but we'll see. So this is gonna return a string, and value. Let's type this, and let's just switch over the value types. Null. Let's group this null with that, and let's also group function with built-in function. Yeah, let's do that. So if it's a primitive, then let's have another function here called primitive. Heap. Actually, we don't actually need the heap. We just need to need a primitive value. The value type, and this is return print primitive value. And for the primitive value, we just check. Okay, so e.type. I think I'm gonna start with null because this is the easiest. You just return null. we just simply return null. And then the second one is okay. So if it's a string, then we just return return v dot value. Otherwise, v dot type is either a number or boolean. We could cast these to string. So string dot value. But I think, let's see. I think I'm just gonna wrap this in quotes. I know JavaScript doesn't really wrap it in quotes, but just to like explicitly, just to make explicit that it's a string, I'm gonna wrap it in quotes. Now we have to print objects and arrays. That's gonna require a bit of a traversal, and then we have to print the functions. I think for these functions, I'm just gonna throw an exception here and say that can't print them. I know like some languages it'll just print something like function and then name or something like that, but for us, like I don't think anybody like is gonna print a function, like even like say JavaScript or Python. But we do need to print objects. So, and here we do need the heap because we need to retrieve the we need to retrieve the key value pair or the values. And then there's also print array. This also needs a heap. Return type is string. I think I'm gonna do print arrays first. So, strings. Okay, so this is going to be a string list that just contains the printed value of all of its elements. And so once we have that, we can just, I guess we could do this. We just join this. For lm of v.lm push print a peep.get element. Okay. That's array printing done. And now for object printing. Objects is a little bit more sophisticated, but you also have strings. Also have the strings array, which is just going to be the printed. It's just going to be each key value pair's printed string. So for const value of let's see, properties. Okay. Object dot entries v dot properties. We just push and the key right here. Actually, hang on a second. Object value properties record string. Right, this is a name. It's going to get coerced. So in the executor, we're going to make sure that the string is a name and not like a pointer. So key and colon any heap get value. And of course, we have to return this EV strings. I guess we'll put the comma here. Okay, so let's run this again. And whoops, we didn't actually call any function yet. So let's go ahead and call the print any function here. Instead of JSON stringifying the heap value, we're going to call print any on it. I guess we also have to pass in a heap. And we can remove this to do. And now we have a problem. Got import module me.ts. There should be a type. These quirks about running TypeScript directly in Node is that you do need to make sure that you do need to make sure that the types are labeled as types. But it looks like what we print is correct. Main. So we print hello. We wrap the string in double quotes, and then we print this number, but we don't wrap this in quotes. All right. So that's the print function fixed. I want to have a look at the AST and also the context and see which one. Next, we have to implement quite a bit here. I think I'm going to do the expressions first. We already finished the primitive expressions, but parenthesized expression is probably really easy to do. I think array literal is probably really easy, and this object literal. So yeah, oh, and also all of these are probably like pretty easy. So I'm gonna do the expressions next. The parenthesized expression context base. Expression, and node is going to be parenthesis expression, and here running a parenthesis expression is effectively the same as running expression statement because you just run the expression within the parentheses, but unlike the expression statement, we do have to bubble up the result the accumulator, but we don't have to do anything like explicit because like after running the expression in parentheses, that executor should set the accumulator to its value. Let's do this, and I guess we can also actually, you know, let's just implement context first. Exec. Yes, with parenthesis expression, move it up here so we don't get a type error. Return this context. Node phase init. parenthesized expression. I can't spell. I don't know why I exported these. We don't actually need to export these. We do need to export this one though. Okay. How is this to work? Well, if context dot type, or the context dot, not context, this should be parenthesized context. Phase is init, just state stack dot push text mode dot expression. We do this, and tx dot phase dot is going to be equal to done. I guess we return if tx dot phase is done. We simply up. So it looks exactly like this. Let's do array literals, export interface, array literal context. Array literal, what is array literal? And here, there's still going to be the init phase, but we're going to take a page out of the call context because you have to compute a list of elements. And we're going to have the LMs array. And then we're going to have something analogous to R computed. We're going to call it LMs computed. And then once we've computed all the elements, then then it's done. So where is exec? Here's exec. If the context phase is in it, there's also a case where the array is just empty, or it's initialized empty. So we have to handle that. If the elements is 0, then we can just transition directly to done. Tx.phase is equal to done. And if it's not, good. And if it's not empty, we need to transition to spell computed wrong. Take that exec stack, and we just push the context of the first okay, so now if the phase is LMs computed, then just like here, we're gonna push the accumulator into LMs. So context.elements.push there. Whoops. And now we have to check, do we keep computing the elements or do we proceed? So we keep computing the elements if the length of the context elements is less than the node elements. And in that case, we just push the context of the next element to compute. tx.node.elements, tx.elements.length. Right, elements.length. The length of this is just the index of the next element to compute in the node. Whereas ctx.phase is equal to computed. Or LMs, or done, I mean. Okay, so now last one is if the context phase is done. And I think for all of these, almost like pretty much all of these context objects, we just like push, or we just pop from the stack if it's done. State.exec stack.pop. So we might also have to do something else. So because array literal is an expression, we do need to like we do need to put its pointer in the accumulator. But first we have to actually create it in the heap. State.accumulator.val is going to be equal to let's set it array, and then the elements is just going to be context.lm. Because like the elements is already a pointer or a list of pointers. So there's exec literal, and I have to put this here. Case. Now object literals, export interface, literal context. Okay, so object literals is going to be kind of interesting because we have to compute both a key and a value. So we can't just like put the key value pairs necessarily. Well, I guess we can do it like this, but we kind of have to like bounce between the key and the value. So we still have this init. So phases we still have init, and then we still have done. But we have to introduce like two more intermediary phases. First, it's I guess key computed, and then it's value computed. So from key computed, we go to value computed, and then once value is computed, then we can track the pair. So we do have to track the pairs, and the pairs. Let's see. I think I'm just going to make it a list of pointer pairs, and we do have to track the key that we just computed. Like once we have computed a key, we're gonna put it in here, and then once value is computed, then we can just like put the key and value. Value is gonna be in the accumulator. We just put the key and the value inside pairs, and we don't. And this one becomes kind of meaningless until the next like iteration. Value computed. Yeah, so let's go ahead and let's actually put this here first. And we'll test. I'm gonna do all the expressions first before testing. So object control. So if ctx.phase is init, and we have to check the length of the pairs because we could be dealing with an empty object. So if the length is 0, and we just transition done. This is equal to done. But otherwise, we have to transition to key computed. X.phase is equal to key computed. And there's actually two cases because a key, if we go back here, a key could either be an expression key or an identifier key. And the way we handle this is a little bit different. So if it's an expression key, we just evaluate it, and then we try to coerce that key into a string. And if it's an identifier key, then we're just going to take the name of the identifier to be the name. So okay, if key type, whoops. I guess we have to get the key first. So this is context node.pairs. And it's going to be the first pair, the first element of the first pair, because we're trying to compute the first pair here. So if the key type is an identifier key, actually, I think I'm going to handle the expression key first. So if it's an expression key, then we can simply push the expression, or the context of the expression, onto the stack. That'll be key.expression. Otherwise, we're basically treating the identifier's name as a string literal. And then we evaluate that and take its value as the key. So I think I'm going to do this, stack. We're going to push the context of this, of a string literal. And the value is just going to be the key.identifier.name. I'm missing something. I'm missing location. We'll just set the location equal to the identifier's location. Oops, key.identifier.location. It doesn't really matter what the location is. This is just kind of like a hypothetical node. It doesn't actually exist. In the AST, just creating it makes our life a little bit easier. And I also realized I forgot to return. Here, that's going to be problematic. There, don't have to return there, but do it anyways. Return here. Okay, so next, if the context phase is equal to key computed, then we get the actually we store the key, we store the accumulator in the key. But I think we need to actually check the value, because we need to make sure that the value is a primitive so that we can coerce it into a string. But the question is, do we do that here or do we do that in computed value? Well, if we do it here, so let's just say like someone does this. Object is equal to, I don't know, let's say this bar. So clearly, like this can't be a key. This can't really be a key, so we need to throw an error here. So on the right side, let's say they call a function. If we throw an error in key computed, then we're not actually going to call this function. But otherwise, we're going to call this function. Now the problem is if we call this function, and like the error, but we're not going to see this invalid key error. I mean, I guess we're pretty light on error handling anyway, so we don't really care like too much how we handle this. I think I'm just gonna like check the value here. So eval is state.heap.get state.eval, and if I think I'm gonna introduce a helper function to check if a type is a primitive. This primitive, runtime value, and this is gonna give us v is primitive value. V is primitive value. Just check if the type is a Boolean or v.type is a number or string, or v.type is null. If it's primitive, eval, or if it's not primitive, we can throw a new error. We can say object key must be. Also, let's just do this. Type, but this. All right, so if the key, so our pairs is pointer because we have to store the value of the key in the heap. We have to store the value of the key in the heap. Actually, I don't think we do. I don't think we do. You know what? Actually, let's just do it anyways. Let's just do it anyways. It's probably not like the best way to do it, but do it anyway. So if it's not a string, then we have to coerce it into a string. Type string and value. I think I'm going to introduce another helper here called core string. And where you can only coerce primitives into strings. So I guess we could switch. Add switch statement here, v.type, cases. In this string case, we can simply return v.val. And in the case of number and boolean, we do this. In the case of null, we just return null. Okay, so coerce string. Eval. So if it is a string, then it's going to get set up here, and we don't really have to coerce it. So now we have to transition the phase to value computed, because we're going to compute the value. Return states. Stack push init ctx. ctx.node.pairs, ctx.pairs.length. Still using the length of pairs to point. We're still using the length of the pairs to point to the next pair we need to compute. And we need to compute the second element in the pair because that's the value. All right, so let's do value computed, and we have to get the value because we've computed the value here. Now we have to get the value heap dx key, or sorry, we have to get the value of the key here. And the reason we get the value of the key is because we have to push its value. So we expect this to be a string. Actually, wait, did I do this right? Did I do this right? I don't think I did this correct. All right, let's actually not write. Let's not actually write this the heap. Let's just take the value as is. So the ctx.key is equal to if keyval.type. If it's a string, we'll just take the value. Key value dot value. Otherwise, we're going to coerce it to a string. And then down below, we're not going to get this key value. We just push the so this key is not actually a pointer anymore. It's a string. And we just push the context key and the accumulator. Once value is computed, then the accumulator is going to contain a pointer to the value onto the pairs. So if now we have to make the decision of whether to continue or not. So if the length of the pairs, and this is what we did for the arrays and also for the call. But if the length of the pairs is less than the node pairs length, it means that there's more value pairs to compute. Otherwise, we can just set the phase to none. Turn. Okay, so in this situation, we're going to bounce back to key compute. And we pretty much do this. There's key here. We have to get the key. This time the key is going to be, so the pair that we haven't computed, so the pair is outlined, key is still in 0, and we just right. That's literal. Let's test this real quick. So let's print 1, 2, 3. Any breakpoints. We'll just print this. Let's remove this. Do. Right. Object literal and array literal. Okay. Turn. Array literal, node, phase net. Return type of literal, node, phase net, and pairs. Yeah, I think I'm actually missing something here. Yeah, I'm actually missing something. I'm missing done. So if this is done, it means we need to write the object into the heap. Then we have to pop. So let's pop first. Turn. Oops. Turn, and then state the accumulator. The value is just going to be the object. The properties is going to be, I think it's object.from entries. Yeah, it should be this. Now let's test that. Print array. Whoops. Return object array. Array. 3. All right, cool. And an object. Actually, let's print. Yeah, let's actually print object foo and bar. Now I'm gonna do this 2. Oh, right, because we haven't supported the binary operations yet, so I can't actually do this. I could probably do this because like this print is going to evaluate to a null. So I guess print 1, 2, 3, 1, 2, 3. All right, so 1, 2, 3, 1, 2, 3. We evaluate this first, and then that's why we printed this. And then this return value is null. We have a null here. And then we have the bar as the right side value. Okay, so let's do some nesting here. So this is an array. Actually, you know what? Let's do this. Let's add some more like stuff. Add some more keys. So I guess K1 is 2, and then K3 is 2 is 3, and let's do more. Let's do nesting here. 1, 1, 2, 2. This. Okay, so 1, 2, 3. That's what this printed. The object is we have null maps to bar, K1 maps to 2, K2 3, K4 maps to this, which just contains a single object with O1, O2. Okay, so objects, array literals, and yeah, object literals and array literals are done. I guess we could also test the parenthesized. Oh, actually, we can't really test parenthesized expression because we haven't did binary operations or unary yet. Let's just see like what we need to support. Okay, so we finished Atom. Binary. Okay, I'm gonna do these next. We already have call, so it's just access left. Okay, for binary expressions, binary expression context. Let's have a look at binary expression type. Binary expression. And we always have that node. Here we already have the init phase, but we need to compute the left-hand side. Oops. And then we have to compute the right-hand side. And then so after the left-hand side computed, after we compute the right-hand side is going to show up in the accumulator. So we actually need a value. We actually need a place here to store the pointer to the value of the left-hand side. And then after right-hand side is computed, then we actually don't even, I think we don't even need to transition this to done. Okay, so left-hand side is computed, we store the pointer here, and then we transition right-hand side computed, and we push the right-hand side onto the exec stack. So we execute that, and then that pops, and then when we get to the next iteration of this binary expression context, right-hand side is computed. We have the left pointer here, and we'll have the right pointer in the accumulator. So we just need to operate on those. And then after we operate on those, we put the result in the accumulator. And then we just pop this context off from the exec stack. So these are all the phases that we need. Let's go and implement. Exec. Expression. Actually, this in the uni here. Type wrong. Exec state, exec binary expression, exec binary expression, context state. Okay, so if the context phase is it, you left. So oops, ctx dot phase. Before we forget, ctx dot phase is to be equal to left-hand side computed. And then ctx dot exec stack. 8 exec stack. Dot push. Init ctx. Init ctx. ctx. I know that left. Right. That's it for that. But the ctx phase is LHS computed. Then we need to store the accumulator. You know, write the accumulator into the left. And let me check the AST again. Okay, so we have to like compute all of these after RHS is computed. There's gonna be a giant switch statement. Oh, I guess there's also these two. So we can short circuit on the, so if the operator is and the left side is falsy, and we don't have to compute the right side, we can just short circuit. On the other hand, if the operator is the or and the left side is truthy, then we don't have to compute the right side either. We can just short circuit. So if the context.node.operator, that and I guess we need to get the left value. So get I think I'm going to choose the helper here. It's truthy. Value. So what do you want to make truthy? I think we're just going to use we're just going to follow JavaScript's rules, which is if the empty string is falsy and 0 is falsy and false is clearly falsy. Whoops. And then null is falsy. And then if it's not either of these, then it's truthy. So return boolean here if v.type is string, v.value is false. Otherwise, if the type is and v.value is equal to 0, we can return false. Comments. Type is boolean, not value, false. And if v.type is null, false. All right, so that is truthy. Truthy, L, and so is this should be not as truthy, because if it's not truthy, we can just set the accumulator to false pop. Boolean value is false. Wait. Pop, because we're done executing it. Otherwise, if the operator that and we are truthy, the accumulator is going to be a boolean. It's going to point to a boolean that's true. True, and then state.execstack pop that turn. But if we don't short circuits, then we have to compute the right hand side. So this is equal to right computed and stack push x ctx. Okay, and then we return. All right, so last phase is if the right hand side is computed, and this one yeah, this one there's going to be a ton of like operators that we have to like do here. So phase is right hand side computed. Now, okay, so the left pointer is going to be whatever is stored in here, and then the right pointer is going to be whatever is stored in the accumulator. We have the left val. This whoops. State.heap.get left pointer. Val is state.heap.get our pointer. And the result is just going to be we're going to have to like fill in the result, switching over the operators. And okay, that's a lot of stuff to implement. But after we've implemented all of that, then result must have been set. And so we can just do this. We can do state.act.val is equal to result up the stack because we're done executing. Okay, so plus so we can only let's see, do you want to support string concatenation? Yeah, okay, so this is going to operate on both numbers, and it's going to operate on both numbers and strings. I don't think we're going to allow array concatenation or object merging. So type is the number. Val.type is equal to number. Then result is state.heap.set type number. And the value is just going to be the left value dot value dot value. I think I'm going to shorten these two to like LV and then yep. Otherwise, LV.type is string. type is equal to string, and we just copy this, except type is not a number anymore, it's a string. And break, but otherwise we throw an error. And what do we want to say in the error? Well, actually, we throw an error in the else. This actually should be an else. So we throw an error, let's say invalid operands or plus. LV.type and RV.type. We break. For the minus, it's a lot easier. It's a lot easier because we can only operate on numbers. So if LV.type is not equal to number, or RV.type not equal to number, we can throw a new error. We just do this basically. That, but otherwise they're both numbers, and so we just set the results their difference, or pointer to the difference. Number value is lv.value, rv.value. I think I'm just gonna like go and implement these, or I'll probably just get the AI to like generate these. Okay, the operators are done. Yeah, that this part was pretty annoying. but I did introduce this thing called primitive equals, which just checks if two primitive values are equal, and this is necessary for the equals, for the double equals, and for the not equals. That's because if two types are different, then the double equals should always be false, and then the not equal should always be true. But the way that we compare primitives and reference types is a little bit different, because primitives we do a value comparison, and for reference types we do just the address comparison. So that's why I introduced this if equal, just to help us check if the values of two primitives. But yeah, this is the binary expression executor. We can go ahead. I'm just going to do some very light testing. So give us 3. Wait a second. Right. Where's pointer? So that's 3. That's correct. And how about, oops, 3? This should give us 7. It should not give us 9. 7. Okay, so good to see that operator precedence is being respected by parenthesized expression. You know, this should give us 9. Okay, so I don't think I'm gonna do any more testing. Actually, you know what? Let's do this. This should be false because, yep, because these are reference types. But I'm just gonna be pretty light on the testing for this, because there's a lot more stuff to implement. All right, let's do unary expression. Expression. So in unary expression, there's going to be 2 phases. There's the is always going to be it. Then there's going to be argument computed. Arg computed. And we don't have to track any data in this context itself, because once the argument is computed, it should be in the accumulator. So we can just go ahead and apply the operator. Right, so context. Exec, I mean, not context. There's the unary expression. There's unary expression union. Turn. did this happen? Very expression context. Okay. So unary expression, if the phase, if the context phase is it, then we set the phase are computed and arg by pushing the arg onto the execution stack. So x and it's just push. So ctx dot node dot argument and turn now once the phase is computed, then you have to go through that switch the switch statement, but this time there's only 3 operators. They're pretty simple. So RHS, let's get the val first. Keep.get, state.act.val. And when I say val, I mean the value of. We still have this result pointer. We have the switch, which is context.node.operator. Case return the results into the accumulator. Data.exec. Go after my results. Oh, nothing. Back up. Is there a squiggly here because it's unvariable? We're going to assign it in here. So here it's keep that set, and we already have the is truthy helper, so we could just set the value to is truthy. Oh. And here result is going to be equal. I guess we have to do a type check here. So if the val.type is not equal to a number, then we do need to throw an error. And what do we want to say in the error? I guess we could say unary minus x begot. Put the unary in quotes. Otherwise, we just negate state.heap sets. Type is number, value is just negative val.value. Break. And here's the same thing, but this time it's unary plus. And we also break, but before we break, result is state.heap.set, type is number, and value is okay. That's exec unary. Test it. True. Got boolean. I think I forgot to break somewhere. I forgot to break over here. Okay, so that's false. Yeah, let's just do this. This should be false as well. Not false. This is true. Okay, negative. Negative 1, 2, 3. And if I double negative this, then it's 1, 2, 3. I'll do 1 plus double negative 1, 2, 3, 4. Right. And plus plus plus. And give us 1. Okay, cool. That's the unary expression done. All right, let's do prop access. Prop access. And for the phase, well, prop access, we just have to compute the target. There's the init. Target computed. And once we compute the target, we just get the property of it. Assuming the target is an object, of course. If it's not an object, we'll throw an error. Yeah. Let's exec that. Actually, let's put the union here. And exec access. So if the phase, do this. Before we implement any further, let's go ahead and do this. Turn exec prop access. Way up here. Where's prop access? Is okay. So if the property access, if the phase is net, then we're gonna set the phase to target computed, and we're gonna push the targets context onto the exec stack. Ctx.node targets. Turn. If the context phase is target computed, then we are we're gonna get the value. So target val. So now, like this target value, if it's not an object, then we can just throw an error. As we want to say here, cannot access property text node dot property of I guess target val dot type. Yeah, let's just say that, and then state the accumulator val is kind of equal to let's get the pointer first to the prop. Where is target val dot property? Name. So if there is so it's either a prop pointer, but if the prop pointer doesn't exist, then we're just gonna set it to null. Or it's gonna return null. I mean, and then state.exec stack.pop. Okay, let's test this. I'm here to do right. Why is that? Oh, right, because we haven't we don't have support for variable assignment yet, so we can't actually do this. But we can do this. I think we can do this. I did not copy this. Okay, so that's a 1. And now if I do B, null. Okay, cool. That's property access done. Now let's do element access. Export interface. Next. So for element access, we have to compute both the targets, and we also have to compute the index. Target computed, and then we also have index So if we're init, then we go and target or set phase to target computed, and then push the targets context onto the exec stack for target computed. And we actually need to store the target pointer here. And we're going to push the index context onto the exec stack and set the phase to index computed. And once we're at index computed, then we have the target, we have the index in the accumulator, and we retrieve that way. Okay, so let's do this. Actually, let's put this in union. I just forget to put this in the union. Okay, so if at this point, this is like kind of mechanical because like we've implemented a bunch of like things that are very similar to this. We need to put the accumulator into the value that's target, that's point to the target's value position heap. Computed state.exec stack push index another index. Now the last part, which is the index computed, where we actually go and like get the data. So we actually need to check the type of the target, because we can only do element access if the target is an array or an object. So if the target, actually we gotta get the value first. L. Yes, target. Now we have the index val, get state val. If the target val is an array, then we need the index val to be a number. The index val is not a number. If it's not a number, then we can just throw an error saying, what do you want to say? Array index must be a number. But got index val.type. Otherwise, we can retrieve the element value, and if this element doesn't exist, then we can just set it to null or state heap.set type null. Okay. Otherwise, if the target val, val.type, if this type is an object, then we need to make sure that the index is a primitive. And then we're going to coerce the index into a string, and then we're going to get the value that corresponds to that string. So so let's check first if it's if the index val is not a primitive, then we just throw another error saying that object must be a primitive got val.type. Okay, target val property is core string. And then we just set the prop to the accumulator. But of course, like that, this might not actually exist. So if it doesn't exist, then we'll just give it a null value. Actually, we don't really need a return here yet. But there's also the last case, which is if the target is not an array or an object. We just throw an error. Cannot access element of val.type. And down here we have the pop. Okay, let's do some testing. Exec element. So let's try this. For 1, 1, 2, 3, 4, 5, 6, 0, 3, 6. So give null. I guess I can also do -1. This is gonna give null. All right, cool. Let's try to give it a string. This is gonna throw an error. Yep, that's throws an error. Now let's do property. Let's try to do element access of a object. So what do you want to do here? Let's say k is equal to like 5 or something. Okay. All right, that's 5. Actually, let's do this. 1, 2, 3. So by 1, 2, 3. So we coerce this into a string. So this should log 5. Yep, that logs 5. 1, 2, 4. Or 1 to 4, I mean, that logs null. That's correct. So if I do null here, and let's get silly. Let's ASDF. This is gonna print ASDF, and then it's gonna print 5. ASDF, and then it's gonna print 5. Exactly. Now let's actually do some nesting. Let's have an array here, and let's have an object here, and let's do a key, which is an array. And so we can access the first element, and then we can get k. So at this point, it's this. It's just this. It's 1, 2, 3, and then k 2, and this is going to give me 3. All right, that's element access done, and that's I think that's all of our expression. Okay, so we did atoms, binary expression, unit expression, access or call. Yep, so that's all of our expression execution done. Now we just have to do the statements. For the statements, let's start with the assignment statement. This assignment context. Actually, I think I'm going to split this into 3 different contexts because there's 3 like. So if you notice, like the left side is an expression, but we can't assign to like every single expression. We can only assign if the left side is an identifier, it's like that, or if it's an object property access like this, or if it's an array access like this. So we can't do something like this. This is illegal. So each of these have their own cases. So we're gonna not have assignment statement context. Instead, we will have what do we want to have? We'll have identifier assignment text, and then we'll have the prop access assignment text. And then we'll also have the element access text base, and so this is identifier assignment. And all 3 of these are going to have the assignment. No, that does mean that we'll have to typecast the left side when we in the executor function. Okay, so let's actually do the identifier assignment. Actually, let's add all three of these. Call this element access. Let's call this element access. Okay, these three. Exec. Statement. Put this at the top where block is. And here we have to check the left type. If node dot left dot type. If it's an identifier, then we're going to return the identifier assignment. I guess we forgot to add the phase. Actually, let's just talk about the phases real quick. So for the identifier assignment context, have the init phase, and all we have to do is just compute the right-hand side. And once the right-hand side is computed, then its value is going to be in the accumulator, and then we can just assign it to the variable in the lexical environment. Now, if the left type is a prop access, then let's see, we have to compute the target. And then we have to compute the right-hand side. But the question is, do we want to compute the target first or the right-hand side? I think we're going to compute the right-hand side first. And then we compute the target last. But I don't really think it matters like too much. Return type prop access assignment mode phase. And for element access is a little bit more difficult, but not more difficult necessarily, but like there's one more phase because we have to compute the index. So it's init. So we still compute the right-hand side first, and then we compute the target, and then we have to compute the index. So let's do this. Now, if the left side is not any of these, then we can just throw an error saying that unexpected assignment target. No.left type. Okay. So we actually need three functions here. And let's just do the identifier assignment first. Identifier. So if the it's init phase is going to be RHS computed, then state.exec push one x node dot right. Okay. If the phase is right-hand side computed, it means the right-hand side pointer is in the accumulator. So we need both the property name and we also need the value. Do we need the value? We actually don't need the value of the right-hand side. We just need the point. So let's have a look at the name. What is it? So it's text.node.left, and I guess we have to cast this as an identifier. I don't remember. So it's name and is this a string? Yeah, it's a string. So I guess we could just do this. Name is equal to that. And then this dot all stack dot peak, because we have to assign it state all stack dot peak. We have to assign it to the environment. Corresponding to that frame. Sorry, not v. It's state dot accumulator dot value. And then we can just flop. Okay. Return. So I think we can test this. A is equal to 5. Let's just see if this works. Yep, that works. A. Whoa. Is that null? I think it's because of this. I need to return this. Okay, there we go. That's 5. Now object. Let's try object. K1. K1. Actually, let's try let's do some reference testing. So if I do like say object 2 is equal to object, then I could do something like this, object 2 true, and then if I do like this, object 2 oh actually we can't actually I wanted to do like this, object 2 dot k k is equal to 3, and then print object and see if this k actually is equal to 3, because it should be, but we don't have support for this quite yet. So let's actually add support for that. It's the prop access assignment. Exo state. Oops. This is sorry, it's not that, it's prop access assignment. Next, state. All right. Phase is equal to init. And the phase is going to be RHS computed. So RHS computed because we compute the right hand side. And I think we can just like copy paste this. Return. Otherwise, we have to put the right hand side in the right pointer, or we have to put the accumulator in this right here. And then ctx.phase transitions to target computed because we're going to compute the target. State.exec stack. Push init ctx. And ctx. Oh yeah, we have to cast it left. Node.left as prop access. Oops, as prop access. Because we have to compute the target. So this is target. And return. And the target's gonna show up in the accumulator. So if the ctx.phase equal to target computed, then we have to, I guess we have to check if the target actually is an object. If it's not, then can't assign to it. So target val, if.get, state.val, if target val.type. If it's not an object, I can just throw a new error. Not set property target val.type. Otherwise it is an object, so we got to get the prop name and the let's see. So ctx.node.left as prop access name dot property. Dot name. And this is the name. So const name for this And target val dot properties name is this. So at that point, we have assigned to the object, and so we have completed executing the property access assignment, and we can just return. And let's test this. A is 3. Yep, exactly. Exactly. So reference types work. Let's just this k object.foo equal to 200. Our object should be k and foo, so k1 and then foo 200. Yep. Let's try some nesting. So foo is let's say it's an empty object. So k.foo dot or object.foo dot p, let's say, and lp 200 under foo. Now if I remove this foo, then this is gonna throw an error. Exactly, cannot set property of null. Yeah. Okay, so the last assignment would be the element access assignment. It's a net, we gotta compute the right hand side. And we can copy paste this once more. Turn. And if the phase is now RHS computed, I think we need to track some values here because we need to track the right. But once we compute the target, we also have to track the targets. So right hand side computed ctx.right is state.accumulator.value. Accumulator to the right. Put the phase target computed because we're going to compute the target. Stack push. We got into CTX of something. So target. We have to do a cast here. Element access. And then we return. Target computed. And ctx.target is equal to state.accumulator.val. And then phase is going to be the last one, which is index computed. And then we're going to compute the index. Push. Just copy this. This target is going to be index. And also don't forget to return. Last phase is index computed. So here we can do an assignment on two different types, either arrays or either arrays or objects. So we have to figure out what the target value is. This has to be an array or object. And if it's neither, then we throw an error. We have index val, state.heap.get, state.val. So if the target val type is an array, now we need to make sure that the index val is a number. So if it's not a number, I guess we can just throw an error. Okay, index must be a number, but guys, so we could just do that. But there's actually another case, which is if we like try to assign something like this, -1 is equal to 200. This is clearly out of bounds, so we gotta check that it's within bounds. So if index val.val, if it's less than 0, or index if the value is greater than or equal to the target value's element length, then we need to throw an error which says, I guess we could say array index out of bounds. target val.elements, and now we do the assignment. Okay. The other case is target val.type objects, and we need to make sure that the index is a primitive. So if it's not primitive, val, and I had an error message above. Not is primitive. Object key must be a primitive. Forgot that. Okay. I do the assignments. And we have to do some string coercion here. Val, yep. And here's the assignment to the object. But there's one more case, which is the target is neither an object or an array, and I think I have an error for that, but I think I'm just going to make a new error message because we're trying to assign as opposed to just access it. So cannot, I guess, assign to. Well, I'm having a much harder time coming with an error message here. You know what? I'm just gonna wing this error message. Cannot element assign to target val type. Okay, so after this, we just pop. And we are done. Let's test this. Object. Do this. Objects first. 100. Go 200. Object K. Very good. Let's test arrays. And this is going to give us an error. Print that. How about 0? 200. Very nice. And let's do some deep nested. Let's do some nesting here. So who is var, which is like 10, 11, 12. So array of 3 is going to point to this object. Who var of 0, let's say. And so this is going to change to 200. And there's the 200. All right, so that's all the assignments done. All right, let's do the function declaration next. So export space. And I think the function declaration might actually be the easiest because all we have to do is just assign. It's kind of like the identifier assignment, except we don't have to compute a right-hand side. Yeah. Cool. And declaration text space. Function declaration. Node is function declaration. Since we don't have to compute any like right-hand side, we can just assign directly. We don't actually need any phases here. Yeah, we don't need any phases here. So let's put this in the union down below. I should probably organize this at some point. I should probably organize this at some point. Go up here. Here's the function declaration. Put it all the way up. We can just return type declaration. Okay, scroll all the way down. So at this point, all we have to do is get the function pointer. And we can set the type to function, and here's the node. Now we need the parent environment, which is just going to be the environment of the top of the call stack. And state, but we have to assign it to a lexical environment. We have to assign it to this lexical environment as well. It's speak.m.set, give it a name. The string, right? Yeah, that's a string. And then let's give it the pointer up exec stack because we already put it in memory. All right, so I think that's actually it. Function declarations. Let's test it. And main. And let's just call main. Oh, we have an infinite loop. Why do we have an loop? Okay, I'm gonna not call this. Okay, we still have the loop. Nope, we don't have the loop. So the problem is where's the execute call expression? Call already. So this is, we haven't actually tested this. We haven't actually tested this. So I think we're going to run the debugger. Actually interesting running this debugger to test our debugger. But let's just see what happens here. Here's the exec stack, here's the block. Next one, function declaration. We have in the heap, have the function right. Okay, so we're gonna execute the block. Okay, actually, hang on a sec. We haven't executed the call expression statement, call. And then the next one should be, why is this a primitive? Oh, right, because we to figure out base call. We have to compute the target first. So the target is a identifier. So we computed the target, and now we don't have any arguments, so call is ready. Okay, now we have block. Okay, so expression statement. That corresponds to this hello. We have a call here, and that's going to call print built in. But we have to go and execute this primitive here, right? And so we finished executing the primitive. Now we computed the. Wait a second. Okay, I feel like that's not correct. Why does it target compute? Okay, let's just keep. Okay, so it's argument compute. Oh yeah, no, I think that's already. Where's printed? So printed is hello. All right, so that's good. Oops. And that's call ready. Okay, so this should not be call ready. I think I missed this part because once we actually finish the call, it shouldn't be call ready anymore. It should be done. ctx.phase equal to done. And I think this is the issue here. Yeah, exactly. So that was indeed the issue. Let's try some more tests. Let's try what do you want to try? How about we try another function? And here, let's declare a variable. And let's, we can't return anything yet because we haven't supported return. Here, I should also print hello, but if I call bar, then it's 5. Let's try this. Remove this. Let's say func is equal to main, and then we're gonna call func. We want to make sure that we can actually use functions as variables. And there's hello. Yep. Let's test closures. So fn outer, and then here's init, and fn actually outer. Let's get return init get, and then I guess O1 is equal to outer 0, and O2 is equal to outer 10, and O1 and O2. And why do I have a to do here? Oh, right. We actually can't test closures yet because we haven't added support for return statements. So I think that's what we're gonna do next. Let's go ahead and add support for, where is the statement? There's the return statement. Go ahead and add support for this. So the return statement is also pretty straightforward. I want to group this together with the function declaration. Where do I put the function declaration? Text. Okay, so export interface, return state, text. Return statement. And here we do need some states or phases, because we may have to compute an expression here. So let's put the, let's just say let's just make the second phase done. So we only have to compute the expression if there is one. Otherwise, we can just pop from init. Yeah. All right. So let's go to exec right here. Return state. I probably should just put all the statements at the top in the beginning. But that's okay. Return. Yeah, we have to put this in the in. What? Return statement. Node, isn't it? Exec return statement. Okay, so how do we do this? We check the phase first. If it's init, then we have to check if there is an expression. And if there is an expression, then we have to set the phase to computed or done, I mean. And then we have to push something onto the exec stack. Context, we got to push the context of the expression. Otherwise, we can just I guess we can just pop it state.execstack.pop. But we do have to set the accumulator. State.accumulator.isReturn is true. And then state.accumulator.val is going to be null, because we're going to return null if there's no explicit return expression. State.heap.set type is null. Okay. Although I feel like we don't actually have to do this. I think we could just, you know what? Actually, let's not even do this. This is a bit too complicated because if there's no explicit expression, then we can just transition it done, and then in done we're gonna set the is return flag to true. I shouldn't think about this. Do we need to do this? Okay, you know what? Let's not get cheeky. Let's just do this. So if context.phase is equal to done, then the accumulator is going to be the return value. We just do this. There that is return. True. And then we just return. So actually, if there is, we could actually just do this. Let's simplify this a little bit. So we don't have to set is return here. We just set the heap null. And that should be good enough. So let's try it. Okay, so here's our what do you call it? Here's the closure test. Our language supports closures now. But let's actually make a simpler test, which is, let's just return something first. I guess we already tested this with the closure test, but let's try this. Let's print like after, and this print should not like, this shouldn't print anything. I guess we could print the main function's output. 1, 2, 3. All right. Return nothing. And let's do let's do this just to make sure that that the accumulator actually got set to null. Yep, the accumulator did get set to null when there's nothing here. And let's actually do this. So after we evaluate this, the accumulator is supposed to be 1, 2, 3, but the return value of the function is supposed to be null. So okay, so that's null as well. And let's actually do the Fibonacci example. Go ahead and compute the Fibonacci numbers. So if 0 or n is equal to 1, then we can just return n. Otherwise, we return fib of n minus 1, fib of n minus 2. And then let's compute the Fibonacci number. Let's compute Fibonacci 3. It should be 3. Whoops. Oh, this isn't. This is the custom language. This is not JavaScript, so there's no triple equals. And we have a to do here. What do you have a to do? Because we didn't do the if statements. Right, so unfortunately we can't actually test this because we didn't support the if statements yet. But do we want to do the if statement first, or do you want to do the loop first? Let me check the statements. Type statement. So we already did all of these. We just need to do a loop, or we just need statements. You know, I think we're gonna do the loop next, and then we'll finish with the if statement. Okay, so for the while loop, so we have to evaluate the condition first, and then if this is truthy, we have to evaluate the body, and then once we finish evaluating the body, we have to evaluate the condition again. And so we're just kind of ping-ponging back and forth. So if it's init, then we're going to evaluate. We're going to push the conditions context onto the exec stack. I guess we also need a cond computed. So what's the condition? We're gonna set the from in there we're gonna set the condition to phase to con computed as well. But if we're con computed, then the accumulator is gonna hold the pointer to the condition, and then we just check if the value is truthy. If it's truthy, then we're going to set the phase to init, and then run the body. And then afterwards, because we're in init, we're just going to go and compute the condition again. So we kind of ping pong back and forth between. But we make the termination decision in con computed. So let's implement this. Case. Okay, so if the context of text is equal to init, phase is condition computed, and state.execstack.push the context of the while node.condition. If the phase is condition computed, we can, I guess, this if it state.get state.accumulator.value. Should actually be not truthy. So if it's not truthy, then we just finish. Otherwise, it is truthy, so we have to go and execute the body. Basically, go to init. State.execstack. Push. Init ctx. We gotta push the body. Do some testing. 0, semicolon. Well, count is less than 10. Count is equal to count plus 1. Count. There's 10. You can also print count in here. Actually, why don't we remove? Why don't we do this actually? Before it actually increments. So 0 to 10. All right. Very good. I think I'm also gonna try. Let's just try. Let's just test the scoping for a second. No, 0. Oh, it's not defined over here. Oh. Okay, maybe using a while loop is not. Actually, I could use a while loop. So actually, let's bring back the count. And we'll set a is equal to 200. I'm gonna print count, and then we're gonna print a down below. So because we're using function scopes, this should be tied to the function or the global scope. We're just kind of like pretending that the global scope is wrapped around a function, and there's 200. Do one more test. Let's just put all this at the function. Oh, whoops, I didn't call it. We don't have to print this count anymore. We just got to print the A. There's 200. Okay, so that's while loops. I guess we could also try nested while loops. So let's I is equal to 0 and A is equal to 0 while I is less than 3, let's say, while J is less than 3 as well, we increment J. Then in the outer, we increment I. And then in the inner, we're going to print, actually print this, I, J, J, and we should not be printing A here. And I think I forgot a semicolon somewhere, probably. here. All right, so I0, J0, I0, J1, I0, J2. I think a little bit weird because we'll have the I1. The problem is that this J is declared at the top level. Also be declared here. And now there's I0, J0, I0, J1, I1, J0, 1, 2. Yep, so that is correct, and now we have loops. Next up is if statements. Okay, so if statements is very interesting, and that's because we have to evaluate this condition and the body, but if this condition evaluates the false, we're not done. We need to evaluate the else ifs, and if none of these conditions hold, then we have to evaluate the else if it exists. Now we could group all of this into a single context, or we could also introduce an else if context. So basically we'll have two contexts. We're going to have the if statement context, which is only responsible for evaluating this condition and this body if the condition holds true. But if the condition is not true and there's some else ifs, then we're going to pop the if statement context and put an else if context up there. And then the else if context kind of does what the if statement does. We just push the next else if statement context if the condition evaluates the false. Otherwise, we just run the body and it's done and so on. So let's actually do that. I'll put it together with the loop context. This if statement context. Sends context base, and the type is notice if statement. And what phases do we need? Well, in the loop we have the init, then we have the condition computed. We ping pong back and forth. But the if statement, so we definitely need the init and we definitely need con computed. But we can't go back to init. Right, we have to either transition to done, or we have to push else if statement, else if context base, and then this is else if. And for the node, well, I guess the else if is not really an AST node. I don't want to do this. I think I'm gonna just put the if statement as the node and just have an index or something. And it's gonna be a number, and it's gonna tell us which else if to execute. And then for the phases, I think we're gonna use the exact same phases because what we're doing is pretty much the same as the if statement, just valuing the condition and then valuing the body if the condition is truthy. Otherwise, we're transitioning to the next else if. So let's go ahead and implement this. Let's go ahead and implement this. Okay, so there's actually a bit of a challenge here, which is we can't actually use this function to create the else if, because this function has to create the if statement. But I don't think that's a big problem. We could just have another function, or in an else if context. All right, we haven't added these two to the context, to the union context. statement, node, and phase init. Have else if, or I think we should call it init else if context. Else if context. And what do we want to pass in here? I guess we have the node, which is the if statement. And we also need an index. There's something, right? We need phase. Okay. There might be a way to group these two there, but I think for now, like I'm just gonna keep them separate. Turn exec if exec state, turn exec statement, ex state, exec else if. And for the if statement, actually, let's just write this function exec else if. The x is else if context, state is state. And if the context is init, and we transition it to condition computed, and we're going to compute the condition. So state exec. And then otherwise, it's condition computed is equal to condition computed, and so we check if the what do you call it? The condition is truthy. So if is truthy, state.heap.get, and the condition is going to be in the accumulator. Then we just execute the body. State exec stack. etx.node.body, and then we set the phase to done. Otherwise we have to otherwise we're actually done executing this, but we have to check if there's an else if or an else. So let's actually pop this because we're not going to execute the body anymore. But if let's say if there is some else ifs. Whoops. Then we have to execute that. So exec stack.push else if context. Make this a bit less verbose. Node, whoops. Node, what? Init else if context etx.node. And that's just the if statement, and we're gonna put 0 for the index. Now, if there's no else ifs, then we have to evaluate the else. So if there is an else, there might not be an else, but if there is one, then we can just well, the else is a block, so we just push the else context onto the exec stack. Yeah. Okay, so then if this happens, if it's done, then we just pop state.exec stack.pop and done. And for the else if, it's pretty much like the same as this, but we do have to fix a little bit. We do have to fix this a little bit because we're not evaluating the condition of the if statement. The if statement, we're trying to evaluate the condition of one of these else ifs. So it's the node.else ifs. Then it's the context.index let's just call this IDX. I call this index, just call this IDX dot condition return. Okay, so if it's condition computed, we still get the value, and then we just, it's not node.body, it's actually node.else ifs etx.idx.body, and then we transition to done, otherwise we pop it. But here it's not else ifs dot length greater than 0 anymore. We just have to check if there's a next if there's a next else if that we could run. So it's ctx.idx plus 1 is less than this, then the syntax is going to be ctx.idx plus 1. And of course, if there isn't an else if to run, then we're going to run the else. Yeah, we're going to run the else. Then if we're done, then we just pop from the exec stack. Right. Okay, so I think this is correct. Let's do some testing as always. Just with a simple if statement. If true, print true. All right, so there's true, and if false. So let's say if true, let's put an else here. True, and we didn't print the else. But if I did false, then we're going to print the else. Now, what if we have some else ifs? Else if, I guess true. And we're gonna print else if 1 if this else if triggers. So if this is false, then this is, so we're gonna print this. Yep. And let's add some more else ifs. Else if true, print else if 2. Okay, so else if 1, let's set this to false, and that's else if 2. Okay. Let's set this to false, and that's gonna be else. Or let's set this to true and check that none of these printed. That's true. All right, so that is that's it. We have if statement support, and that's actually it for the executor. We're done with it, and we're actually done with the debugger now. But let's just do some final tests. Let's get the Fibonacci. Let's get the recursive function to compute the Fibonacci number. N is equal to 0, or n is equal to 1. We just return n. Oops, forgot to type in there, and then we return fib 0, or fib n1 plus fib n minus 2. And we can print fib of, let's do 3 first. So it's 0, 1, 1, it should be 2. Okay, so there's 2. And I think the 10th Fibonacci number is 55. So let's see. Okay, so we got 55. All right, cool. All right, so that is the executor. I think actually I'm gonna do some more testing, and I'll probably run this through AI. So I'm gonna do a little bit more testing, and after that we can move on to the more visual front end part. Okay, let's do the front end now. Here I have a very bare bone React project that was scaffolded with Vite. So as you can see, there's like pretty much nothing in it, except the hello world. So let me go and open this in the browser. Yep. So I also went ahead and copy pasted all the code for our interpreter here. Now our first goal is to be able to run some code and display the printed values on screen. So for that, we are going to need 3 components. We're going to need a code editor. We're going to need a component that displays the code, and we're also going to need a controls menu where you can actually click the run button. So I think I'm going to make the output first, because that's probably simplest. So let's call it out, and for the props, all we're going to receive is just a printed array. And I guess we can also receive an on clear to clear this. Return div, whoops. Return div, and we're not gonna make this look pretty. We're just gonna try to get something working. H1 output. Let's just give it a header, and then I guess we can also make a button over here, which is clear, and then click is prop stock clear. Whoops, prop here. I think I'm also gonna give this button a little bit of a margin on the bottom. Again, we're not gonna make this pretty right now, but we will prettify it at the end. So props.printed.map the I, and I think we're going to use a pre here because we want the text to be formatted. React is going to yell at us if we don't fit E. And here we're just gonna maybe V is not the right. I guess we'll just call it line. There's our out component. Let's put it in our app. And let's actually put this side by side. So the flex box here and out. Go printed. For now, we'll just give it an empty array and on clear. We nothing for now. Let's go ahead and browser. There's our output. Now let's make the code editor. And for the code editor, I'm actually going to use this library right here called React Code Mirror. And this is a React wrapper around the Code Mirror library. I think this editor is actually really good. As you can see, this is a demonstration here. There's all these extensions, line numbers. You can enable them. You can disable them. There's also fold gutter, and it's got highlighting if you want to enable that. So to install this, I'm going to just go to the npm package and let's go ahead and install it. Okay. And we can also copy paste some code. Scroll all the way down. Let's so this is the line that we're looking for. Make our code component. Let's just return this. Whoops, that, and let's import this code mirror. I guess we could also call it code mirror, but yeah. Actually go ahead and delete this, and I think if I just render it like this, it'll actually work. But of course, we're not gonna be able to access the values that have been typed so far. So this code, import it, code. Let's go back here. Crash. Oh, whoops, we didn't run dev this. Okay, so we have this code mirror, like box right here. Of course, we want to make it a little bit wider, so let's give it some width. Width, make it 400, and let's refresh. Okay, so now we have some width here, which is good. Yeah. Okay, so let's talk about the app state. In the app, we're going to track we're going to track the code, and we're also going to track the values that have been printed by the that have been printed. So let's make the state here, and code, and here's printed. I'm actually going to call this base state because later on we will have to modify this a little bit to support breakpoints and to support like seeing the call stack and all that like funky stuff. But for now, this is all we're going to have, and let's just create the base state. Okay. Whoops, sorry, this is not state, this is base state. And for the code, I think we're going to just default with a bunch of new lines. Just so that we can give this thing some height, because if I refresh it, it's got like no height. And then printed, of course, is going to be the empty array. Now code is also going to receive some props, code props. It's going to receive the code, of course, and then it's going to receive an on-change handler, which is, I guess, new code. There's the string, or yeah, oh sorry, there should be a string here. Or why don't we just make it less verbose and just call it code. And props change is props dot on change. And whoops, I spelled that wrong. And let's give it a value of props.code. So here, let's code. Code is state code, and on change. Where all we're going to do is just set just going to update this. Why is this happening? This should be a type void. Okay, there we go. And just for good measure, I guess we can just print state. This up. There's that. And let's update it a little bit. Yep. So as you can see, the code here is changing. All right. So now let's add the controls. And what controls is going to have is it'll just have the run button. And I guess we're also going to add a stop button, because later on we will need it to stop the program from executing once it has paused at a breakpoint. So return a div, and I guess we can make this a flexbox. Run. Stop. The props. On run. On stop. And stop is going to be optional, because we only want this. We only want to stop if the code is actually running. But this is only, like, we're only going to need this once we start adding support, or once we add support for breakpoints. Go props. On run. Click. On run. And I guess we can put a disabled here, which is props dot on stop. We don't want users to click this if we don't have an on stop. Okay, so let's put this in the app. And I think I'm going to put a div here. I'm going to put the controls right under the code. Controls. S here, plural. And for now, on run doesn't have to do anything. Let's look at how our app looks. Here's run, and here's stop. All right. I don't think the disabled quite works here. So actually, let's just remove this for now. But yeah, now we have the UI. When the user clicks on run, what we want to do here is we want to compile the code and then receive an instance of the executor. So over in our interpreter, we have this executor in run, and we have this exec function. So let's actually do this. But actually, before we can execute this, we need to parse it, and we need to parse it first. So let's do this. Const tokens, Tokenizer, and then new Tokenizer, and then state.code dot tokenize, and that's going to give us the tokens. And parser is new parser tokens, and here's the AST is parser dot parse, and then we can create the executor. So const executor, or I'm going to call it exec because our function is called executor, AST. And now what we can do is just exec.advance. We look into the advance function. It just returns the state, and the state is just currently printed. Later on, we will have to we will have to return the heap snapshot and the stack snapshot and whether the program is finished or not. But for now, since we just want to get code to run and to log the output, this is sufficient. Okay, so exec.advance, and this is going to be the printed so far, and state that I guess that's state whoops, the state and printed, and that should show us the output. So we can implement on clear. Let's move this a little bit. Let's implement these two now. Printed is just going to be state.printed, and on clear is just set state, and this dot state printed is empty. Okay, there we go. Let's now try this. So if I print hello and I run this, we see the hello. And let's clear this. Let's print world, and we'll see the hello world. Now let's have let's actually print these two, but let's also make a count variable here. And then while count is less than 10, count is equal to count plus 1. Let's just like have our counter here. Counter print done. The end of it. All right, there we go. So this code is now executing, and the outputs are now being displayed. Next, we're going to add breakpoints. So to do that, we first need to make it so that if you click on one of these lines, then you can see like a red circle here, and that's going to be the line in which we're breakpointing at. And to do that, we are going to plug in to this code component right here. There's going to be an extensions property that we have to fill out. So let's go ahead and create the plugin. I'm going to create it in a folder called code mirror, and I'm going to make a file called breakpoints.ts. And I think I'm also just going to copy paste some code, which is pretty like typical when you're integrating with a third-party library, but and also explain it. So the way that this kind of works is that in code mirror, and also I should put a disclaimer here, is that whoops, I'm not really an expert on this library, but from what I got, there's this thing called a gutter marker, which is just like a sort of decoration or like widget or HTML element that you put on this left side. The left side is what we call a gutter. And then there's this thing called a state field, and what the state field is just it just manages like all of the gutters or all of the markers that you've put on the gutter. And this update function gets called every time there's like a change to the editor. So if I console log this, you'll see that this editor tracks like pretty much everything. If I click here, whoops, let me refresh. Okay, I didn't load the extension in to the editor, so let's do that. Breakpoint gutter. Okay, now if I go back here and I refresh the page, and if I just click anywhere, you can see that we're logging stuff. So that this editor like tracks every click, it tracks like every highlight, it like pretty much tracks everything. And the update function over here gets called every single time. that there's an update of some sort. And so there's also this effect, and this effect is just kind of like an event that propagates some data, so that you can manage the markers. In this case, our event is custom and specify the line number, and also whether there should be a breakpoint or not. And here we're iterating through transactions.effects. A transaction have a list of effects, and we want to find if there's a breakpoint effect, and we want to check the on. If there is an on, then we have to add a breakpoint marker to the current line. Otherwise, we have to remove it from that line. And then down here, this state is actually supposed to be an extension. And then there's also this gutter extension right here, which kind of adds a column to this part. So if I actually click, then you can actually see the red dots here, and that's going to be the breakpoints. Now, you do need markers. This is like all the breakpoints that are like currently on your gutter, and then this initial spacer. This kind of gives the gutter its width. If you don't have this, then the gutter is going to have, I believe. And then of course there's the event handlers and the mouse downs. Like a line, then this is the code that toggles the breakpoint. So we can do breakpoints now. We now need to make breakpoints available to app, because currently we only see it on the UI, but we don't actually track the state in app. So let's put breakpoints, and this is going to be, I believe it's going to be a number array, and this number array is going to be the line numbers, or going to contain the line numbers. So let's go ahead and default that to 0. And because CodeMirror is not native to React, we can't really easily synchronize the breakpoints with it. So we can't just say breakpoints here is equal to say props.breakpoints or anything like that. We can't do it that way. Instead, what we're going to do is that every time there is a breakpoint change, we will propagate up all of the breakpoints that exist into app. So from here, we're going to pass down this thing called on. We're going to pass down this this function called on breakpoint. And what this is going to do is that it's going to take a list of breakpoints, and it'll just set the state. It'll just update. Whoops. Wait. Breakpoints. Yes, it'll just it'll just update the breakpoints basically. We have to add this to the props. BPS number void. Now in the editor, we are going to have this on update function, or on update prop, and every time it updates, we do need to find all of the breakpoints that currently exist on the editor, and then propagate it up. So again, this is an integration, so I'm just going to copy paste some code here. Every update is whoops. We need to import the breakpoint effect, or export the breakpoint effect. We have it exported. Breakpoint effect, and here's breakpoint state. So every time there's an update, every update contains a list of transactions, and each transaction contains a list of effects, and we just have to check if the effect, the breakpoint effect, is in here, and if it is, then we're gonna collect all the breakpoints and propagate it up. We also need to check if the clock has changed, and that's because if I go back here and I set a breakpoint, and then if I hit enter a bunch of times, CodeMirror actually automatically moves the breakpoint down. But if we don't if I press enter, like this effect is gonna trigger an update that doesn't contain a breakpoint or remove a breakpoint. And so let me actually just console log to demonstrate this. And let's just remove this. Actually, let's keep this for now. So let's refresh the page. I'm gonna put a breakpoint here. But we see that every time I press enter, there's the breakpoint just shifts down. But if I don't have this update .doc changed, and then I put a breakpoint on line 5, and then I push enter a bunch of times, in the editor, the breakpoint actually shifted down. But as you can see, we don't actually detect that change. So we do need this update. We do need to check if the document has changed. Okay, now we have our list of breakpointed lines propagated up to app. We have to convert these into AST node IDs, because if we look at the executor only accepts breakpoints as AST node IDs. Now, this executor actually allows you to breakpoint on any node, but in practice, you're probably not going to breakpoint on, for example, identifiers. You're probably not going to breakpoint on object literals. So the way that we're going to turn these into AST node IDs is that we're going to map each breakpointed line to a statement that starts on that line. And if no such statement starts on a line, then we're just going to ignore that breakpoint. So let's go ahead and make a function that does that. So function, and we're going to call this get node breakpoints. And here's breakpoints, and this is going to be the lines. And then we have a program, which is our block. We can also call this AST. We're gonna call it program, and this is gonna give us a list of AST node IDs. Whoops. Okay, so that's fine. Set. We're gonna put this into a set, and so we're going to do a pre-order traversal on the AST, and every time we map one of these breakpoints to a statement, we're just gonna remove it from the set because we don't need to map it again. And then we also need to track the AST node IDs that we have already obtained. Yeah. So let's create our walk function. And this is going to take the node that we're currently on, and we just switch over it. So we only really need to visit the we only really need to visit statements, and we only need to traverse down the bodies. So for a lot of these nodes, like say array literal and object literal and these binary expressions, these are never going to have bodies as like a child, like a nested child. So we can simply just ignore these, but we do need to handle the block. So we're going to have to walk each statement in the block. So let's do that. Statements, and we have to check first if the remaining has, and remember we stored the line number in the location for each node, and this is where we're going to use that. And nodes.add statements.id. So we've mapped the breakpoint or breakpoint line to this node, and we can also remove it from remaining line. Okay. And then we have to walk the statement itself, because if the statement is like an if statement or a while loop or function declaration, then it is going to have a body. Actually, let's just remove everything down below, because none of these are going to have bodies as a child. I guess we also need to put a break here. If statement is we just walk the body here. And then we also have to walk the bodies of every else if, as well as the else if it exists. Const else if. We walk else if dot body, and then if the node has an else, we're gonna walk that node as well. We break, and then for these two, we're just gonna walk their bodies. And I guess we're just gonna put a break. We don't really need that. So this is going to give us, this is going to populate the node once we call it on the program, not the block. And we can just return the array of nodes. So get node breakpoints, where we're gonna call this is over here on run. So here's our AST, and then we need to check the breakpoint nodes. Just get node breakpoints, state dot breakpoints, and also state dot or also AST rather. And then for each of these breakpoint or breakpointed node, we're going to actually we have to create the executor first before we do this. Executor exec dot add a breakpoint for the ID, and now each time this advances, it's going to just stop at whatever breakpoint that we have. But we're not quite done here. There's quite a bit to do, because in the state we now have to section the state into two types. We need to distinguish between idling, so there's no program that's running, and then we also have to distinguish, distinguish the executing state. Space state type executing, and in the executing we actually have to track the program itself, because like as the program is executing, maybe the user adds a breakpoint, maybe they like remove breakpoints. So if that happens, then we have to reset the breakpoints in the executor. And so we have this clear breakpoints method here. Of course, it's not the most efficient way to do it, but it is a pretty easy. Choose the easy way out. But let's go ahead and implement this for now. And actually, we just need to track the program. And the state right here is going to be either idle or it's going to be executing. Let's start with idle, because in the beginning, nothing is running. And then on run, so this run button can be clicked whether the state is idle or it's executing, and its behavior is going to differ. So if the current state is idle, then we do have to parse, and then we have to create the executor and so on. But if it's not idle, then we do need to like track this executor somewhere. So we're gonna do it in a ref. It's actually bad practice to put an instantiation of a class in the state. So I'm gonna use a ref. Use ref. Whoops, sorry. Executor ref. Use ref, and I think I'm gonna export this just for the typing. Executor, and we're just going to default this at null. So if state is idle, go ahead and do this. So executor ref dot current is equal to exec. All right, and so here is where we get the nodes. In fact, let's actually make this even simpler and just do this. Add the breakpoint. And I think now is the time where we have to signal whether the program has finished running or not. So let's actually introduce an execution state, which is gonna be more than just a set of printed lines, but we're still gonna have printed. But now we need the finished flag. Let's return this. This we printed, and finished is just going to check if the exec stack is empty or not. If it's empty, it means the entire program must have finished running. So this.exec stack.lang 0. Okay, now we can tell. Now we can tell whether it's finished or not. So user clicks run. We run until we hit the first breakpoint or until we finish. and this is not printed anymore. This is like exec state. So if the exec state is finished, then we're gonna do something. And if the exec state is not finished, we're gonna do something else. If the exec state is finished, then we need to set the state to idle. Type idle, and then like we can like keep the code, which is state.code. We can also keep the breakpoint, state.breakpoint. And then printed, I guess we could just append what we have imprinted with whatever got printed next. State just to keep the logs from before, and let's remove this. Now, if the exec state has not finished, then it's hit a breakpoint. So our type is going to have to be executing, and we can keep the code, we can keep the breakpoints. I guess we can just copy paste this right here. And then we also need to track the program. So where's program? Would just be, I guess, AST. Actually, let's just rename this thing to program. Just okay. So that's what happens when the state when the run button is clicked when the state is idling. But we can also click the run button when the state is not idle. So if the state dot type is if it's executing, then we don't have to create this again because we already have the executor in a ref. Oh, and also I guess if it's finished, we need to like remove the executor here. So executor ref.current is equal to null. We delete the executor here. All right, so down here we can just get the I guess we'll call it next. Actually, you know, let's call this next over here, and we get the next state executor and then we also have the two cases, which is if it's finished or if it isn't. And if it's finished, then we need to reset the executor ref. Otherwise, and we also have to change the state to idle. We have printed, which is dot state dot printed and dot next dot printed. Code stays the same. So does the breakpoints. Okay, so the other case is, oops, that state, and the type is going to be executing. We can copy paste this, and then the program is just going to be whatever the program of that state is. Okay, so this is the on run handler. Next is where's the on breakpoint? So on breakpoint, we can't just set the breakpoint and call it a day anymore. We actually have to update it if there is an executor ref. So we first check if there's an executor ref, or we can also check if the state is executed. But I think it's safer to do it this way. Now we also have to have this loop in here. So it's state program. I guess do this state dot type is equal to executing, and then we have executor ref breakpoint. I guess actually let's code up a little bit. Let's do this executor ref.current. We're not going to have this. Yeah. So okay. Are we missing something here? No, we're not. Oh, I guess we are because we have to actually clear the breakpoints before we add the next breakpoint. And then of course we have to do this. So let's see. Oh yeah, actually one more thing is we need the on stop here because we do have the on stop. So if that's run on stop when the world happened here. So if the state is executing, then we should propagate down the onStop function. Otherwise, we don't have anything. And this is just going to clear this. And it's also going to set the state to idle. Okay. So I guess we kind of removed the disabled, but let's bring back the disabled. I think last time I put a double exclamation mark here, but it should one. There's no on stop. Then it's the same. Okay. Go back here and let's try to. Let's actually first. Oh, why did I print? Okay, let's actually remove the print statement first. In code.tsx. The console log, I mean. And now let's add the print statement here. And I'm just gonna run it just to check that we still run the code. Okay, so we can still run it. Let's put a breakpoint here. Let's put a breakpoint here. So if I run this, okay. So actually, let me refresh this page again. Let's run this one more time. So one. So if I put a breakpoint here and then I run it, then it's gonna hit this breakpoint. And then if I run it again, then it's gonna execute this, and it's gonna hit this. And I can execute it again, and now this program is done running. So as you can see, the stop button is grayed out. That means we're back in idle state. And I can also just add some extra lines up here. And remember, the code mirror automatically pushes down. And because we have the on breakpoint method, we have this method right here that pretty much like synchronizes the breakpoint with the executor. We mount the executor with this. Then we can just run it again, and we'll persist the same breakpoints at the correct statements. There we go. Let's try the more sophisticated program. Count is equal to 0 while count less than 10. 1 and done down here and over here. Set a breakpoint here, set a breakpoint here. Count. Check. I'm not quite sure what happened there. I think it was probably some like lingering like print state or something. We might have to debug that in a bit. But let's try. We breakpoint here. We didn't print anything. Now we print the 1, and now we print the 2. We print the 3. We print the 4, and so on. So if I remove this breakpoint, then the executor is just going to run up until this 5, 6. Okay, I guess it didn't. I guess that didn't happen. So we have to do a little bit of debugging here. Okay, so I found the issue. That the problem is this. We're using the we're not using this updated list of breakpoints. We're still using the breakpoints from this state. So if I set BPS here, then this should fix the problem. So let's this here, go here, go here, and I run this 1, 2, 3, and I remove this breakpoint, and now it's gonna go here and that. So let's actually run this again, but this time, whoops, clear this, and now we're going to just remove all of these, both of these breakpoints, and run into a completion. And now let's test the on stop. So I go here, I run this, I run this, I run that, and then I stop it, and then I run this again, and then it's going to start from the beginning. The stop actually does work. All right. So here, so we now have breakpoint support. The last thing that we have to do before we can give this like a CSS makeover is to render the call stack. To render the call stack, we need the heap and the stack snapshots. and we're gonna have to return it in the execution state because right now, like we kind of just we don't have that information at all. And I'm gonna make a diagnostics file right here, diagnostics. Yes, and this is going to contain um, two functions. It's going to contain this thing, stack diagnostics, which takes as input the call stack, and then produces output diagnostics stack. So that would be like the stack snapshot. So diagnostic frame will have these fields. We're going to have the frame ID. We're going to have the function name. We're going to have the location. We need the location because we have to highlight the piece of code that is currently paused on that stack frame, or for that particular function call. And we also need the set of local variables, which we're going to derive from the from the lexical environment of that frame. This is going to be a pointer, so let's return a list of diagnostic frames. We get the entire stack, and then we just map each frame. The ID stays the same, the function name stays the same, and the location also stays the same. Then for the local, what happened here? Cur, right? It's cur. Cur. This is the node that it currently executing for that frame. So local, we need to. I think I'm just gonna clone it. I'm just gonna structure clone the entire environment here. Probably the most efficient way to do it, but it works. Now let's generate the heap snapshot. Heap snapshot. And the heap snapshot is going to look almost the same as the heap. Let me pull up the heap. Where is memory? So it's going to contain all of these runtime values, with the exception of functions, because it's not really obvious how you would render like an input, like the AST node for one. So we're going to scrub out the value, and we're going to introduce this type called the value. It's going to just be the runtime value with the exclude. But we're going to have this external value. And all this has is just this type right here. So the external value is the runtime value without the function. And then the heap snapshot is just going to be a record of pointers to external values. Of course, that's going to be derived from the heap. So we can create a snapshot. That's from entries. So we're going to get the entire heap here. And then we're just going to map the key value pairs. A, B, A, comma, E. So key can stay the same. Whoops. Sure. Text error here somewhere. Okay, so we have a key. And then for the value, if v.type function or v.type is a built-in function, then we're just going to stub it out for our external function. Otherwise, we're going to keep the value. And then we're going to clone it. That's our heap snapshot. So let's return to run. And I just noticed that inside run, we don't actually update the per in the stack frame. So we don't actually update this value, but we should be updating this right here. And it's quite simple. call stack dot peak dot cur is equal to cur dot node. Right. Go. Now in the state, let's go ahead and add the stack, which is just contain the diagnostic frames. And then the heap is the heap snapshot. All right, so we have this, and I guess we have here. So heap is snapshot. Heap stack is stack, not snack. Stack diagnostics. Diagnostic stack or call stack. Okay, so now we have the heap. We have the stack. We only need to track the stack if in the app if the state is executing. So if the stake stake if the state is executing, then we'll have this diagnostic frame. We'll also have the heap snapshot. And let's go ahead and add that here. Heap would just be the next stack here. Okay. We're going to now add the stack here, so we'll just call it the stack.exx. And for now, I guess we can just play like just a header here. But stack, and I think actually going to give it a little bit of margin. And let's just bring it into the app. We'll add the props later. We'll put it, where do you want to just output? I guess we'll put it on the right of output. Stack. See that it up here. Okay, so here's the stack. I give the stack some margin on the left as well. Again, like not trying to make this pretty. Also not trying to make the CSS maintainable. Just trying to get something to work. Let's add the props for the stack. Stack props, and the stack properties. We're gonna have to give it the heap snapshot because it will have to show all of the values in the stack, and we're also gonna have actually for the stack itself. I think I'm gonna do this. I'm going to introduce this thing called a input frame. And this is just going to look very similar to the diagnostics frame. So function string. I think I'm also gonna this type is equal to frame ID is equal to string name, and here's our local variables, our name, and it's a pointer. But we're also gonna have this thing called expanded, and this is if there's an object, then you'll be able to click on it, and it'll show the object expanded. And to track like which objects have been expanded or not, we're just going to track it by their pointers. Then there's this thing called a rendered frame, which is going to contain the frame ID. It's also going to contain the function. I think we're just going to call this name actually of the stack, which is the same as the name of the stack frame, which is the same as the function name. But because we're going to render this frame, we need a list. We need this expanded, we need the local variables plus any nested values that are expanded in a list. So it's going to be a list of entries, and then the entry itself is going to have a name. So that's like the variable name. It's going to have the value, And then this value is going to be a stringified value. So if it's like an array, for example, then this value is gonna be stringified into this, or if it's like an object, it might be stringified into that. But every value is going to be stringified. And then we need the pointer in the depth because we need to render some padding on the left, depending on how deep this this value is. And also we have to check if it's expandable. Because we only want to expand objects and arrays. We don't want to expand like any primitives. There's like nothing to expand. So that's the entry interface. And so let's props stack is going to be the input frame, a list, and we have to have this function called flatten, which takes which basically takes the local variables and also the keep snapshot and expanded record of pointer and I think Boolean. Let's move this right side. Boolean, and it just returns a list of entries. So entries, and this is another like a pre-order traversal. This is gonna pre-order all of the local variables. Pre-order, and going to be a name. There's going to be a pointer. There's going to be a depth, and we can fill this in a little bit. This is a number. So how this is going to work, or how this is going to get called, is that we're going to iterate through the we're going to iterate through local. Local, and then we're just going to call pre-order on the name and also the pointer, and then the starting depth is going to be 0, and then this pre-order traversal is going to fill out the entries. So afterwards, you can just return entries. So first, we need to push the name, and then we also need to push the value. But again, value is the entry, or rather, value is a string. So we have to get the heap value at this pointer location and then coerce it into a string, or yeah, we have to turn it into a string for rendering. So here's the heap value, and I think I'm going to introduce stringify function. Takes as input an external value. Value produces as output a string, and we can just switch over the type. Here I have a bunch of case statements. So if it's a string, it's a boolean, it's a number, we can just return. I think we just return this v.value. Or maybe for a string, we might want to wrap it in quotes. Return. And then for the object, we want to actually, let's put null here. Do null first. This is really easy. Just return null. For an object, we're going to return this. And for an array, we're going to return this. And for a function, I think we're going to return, what do you want to return for a function? Probably just this. And we can call stringify over here on the value. And then we have to give it the depth. We have to check if it's expandable. It's only expandable if it's an object. Object, or it's an array. And let's also include the pointer. It should be entries.push. All right, so if v is an array and expanded true, so we only expand if the user has clicked this particular element, then we're going to pre-order. And the name of this, I think we're just gonna let it be the index. Whoops, I have to put a loop here because we gotta loop through all the elements. elements length 1 and pre-order. And so the name of this, I guess the ith element, I guess we'll just call it I. And then the elements I, and then the depth is we're gonna go one deeper. Now the other case where we want to expand is if it is an object. So we iterate through all of the key value pairs, and we call preorder. In pointer depth 1. All right, so that's our pre-order traversal, and this is going to create the entry for us. So let's so we're going to have to map each input frame into a rendered frame. So let's do that. Frames is rendered frame, and this is going to map prop stack. ID stays the same. Name is just the frame function, and the entries would just be we flatten the local, we give it the heap. All right. And now we can just map these frames and actually render them. Not entry, it's frame. Sorry, it's not entries. I'm not sure why I put entries there. Let's div key is I. Yeah, so key is, I think we're going to give each of these a border. And its border, I guess, is 2 pixels, solid gray. Not. Let's put some padding. And I think we can also render the frame name 4. Now we render the entries, the entry map, and this is why we flatten it, because now rendering the entry. It's div e just be ij. I think we are going to put in a span. Name. But we also need a colon here to entry the value. We can put this in a span. We can put the value in a span. Actually, you know what? Let's just do this. Name colon entry value. All right. So we're gonna handle expansion and collapsing in a little bit. Let's just get something deep. Just state. Actually, we're not gonna have access to the heap if the stack is idle. So I guess we don't really have to render the stack if the state is idle. But I guess we might actually let's just render the stack, because if the state is idle, then there's going to be nothing in it. So state type, if it's idle, then we can just give it an empty heap. Otherwise, give it the actual heap. And then the stack. I guess we have to turn each stack frame into an input frame. So actually, let's just export this and let me see the diagnostics frame again. Diagnostics frame. This. right here, it's pretty much the same thing, except there's a location object right here. We don't actually need the location object because the stack is not going to be highlighting any code. But let's just do this for now. Is equal to state stuff. I guess we have to check title or not. It is, give it nothing. And if it's not, then stack.map, state.stack frame. And I think I'm just going to destructure the frame and give it an np expanded. All right, so let's go ahead and make some. Let's just do this first. See that there is a stack. Okay, so there's stack. Why is there a here? That should be in the built-in environment and not the global. Actually, let's try another example. May have to debug that one, but print. Oh, let's actually add some variables here. A equals 5, and we could do C is equal to 15. Breakpoint here, call breakpoint here, and we have the print here, which is kind of weird. But let's just go to the next breakpoint, which is going to be here, and let's see if the stack is correct. So C is in. All right, so we show all it shows all the variables. Okay, so run. Right, because we set in the global env, we should have set this in the built-in env. Whoops. Built-in env. Okay, let's refresh this and try again. Run. Okay, now we don't see the anymore, and then we print. Oh, and now the stack has been popped. So that is good. Let's try some objects now. Of course, we can't expand objects. I guess we can also add some arrays. Free, foo, and bar. 1, 2, 3. Yeah, let's just do that. Run this. So we render the array, we render the object, continue, and stack. Okay. Now let's try one more. Oh yeah, I guess we also print foo. Let's do the Fibonacci numbers. 0. We return 0. 1. We return. 1. And I think I'm going to destructure the left and the right so that we can breakpoint on them. Turn left plus right, and then we'll call fib on 3. And do you want to print it? No, I don't think we need to print this. Let's put a bunch of breakpoints everywhere. Run this. So we're breakpointed here. We haven't highlighted it, so it's kind of hard to see. But fib 3, and then fib 2, and then fib 1, we should have been breakpointed here. Now we're going to backtrack, and left is now 1, so we're going to call this function, and then it's going to be 0. So we're breakpointed here. We backtrack, and now this right has been computed, so we breakpoint over here. And now left has been set to 1. We have to compute the right. Go to fib 1, so 1, fib n equals 1. And so we breakpoint here. Let's keep running. 1 plus 1. We're now at this breakpoint, and it's we're done because we've already breakpointed here. So when we return, we're not going to breakpoint here again, and our program has finished executing. So we now can render the stack. Let's go ahead and add expansion functionality. To support expansions, we're going to track we're gonna track a field here called expanded, and it's gonna be a record of frame IDs. Did I export frame ID here? I did not export frame ID. So it's going to be a record of frame ID, and then for each frame ID, we're going to store the pointer that's been expanded, and we want to keep it here. We don't want to put this in like the stack, because if we continue running, then we don't want to collapse the already expanded variables for the previous frames. So this expanded. Actually, is this empty? So this is when the state is idle. Okay, so yeah, this is empty, but this right here, we need to get so expanded is going to be the current state's expanded. All right. Now we have to fill this out. Let's actually hang on a second. There's not going to be enough space, so let's down a little bit. Or actually, where do you want to expand this down? Let's expand this down like this. So it's state expanded frame.id, and if this doesn't exist, then we'll just default it to empty. Now in the stack, we do need an on expand function. And I think we're also gonna propagate down the actually, you know, let's do this. ID is the frame ID, and then the pointer is just the pointer, and this is going to be this is not going to return anything. So on expand ID and pointer, and all this is going to do is it's just going to add the pointer to the actually, we're just going to do this. So I guess we also have to check if the state is executing. If the state is executing, then set state. Actually, how do I want to do this? Actually, I think I'm going to do it this way. I probably should have installed Immer to make this look a lot nicer, and also simplify this a little bit, because the React compiler does automatically memoize a state, so you can't just like update like the expanded in place. You actually have to replace like this entire expanded, or at least you have to replace. Yeah, you have to replace this entire expanded, but you also have to replace like this. So let's do it this way. State.type. If I had Immer installed, then that wouldn't like be too bad of a problem. Expanded. State.expanded. If not expanded. Empty. A lot of like copying here. ID and pointer is equal to not expanded. ID pointer. And then we just return the state, which is whatever state is and expanded. And this is only when the state is executing. If the state is not executing, we'll just return whatever the previous state was. And now here we have to make use of on expanded. So I think we're going to set an on click handler over here. Yeah, we're gonna set an on click handler over here. And so if the entry is expandable, then we're gonna call props.onExpand on the frame ID, and also on the entry.pointer. Yeah, also on the entry.pointer. Let's try this. Actually, this is not a good example because there's nothing that can be expanded. So foo 1, 2, 3. Let's do this. Or 4, 5, 6. Okay, and we can just print the A here. A breakpoint. Okay, so we expand the A. It's foo. Okay, we forgot to add some. We forgot to add the padding. So let's add some padding here. Padding left is going to be entry.depth. I think we're just going to multiply it by 10, see how it looks. Okay, so we multiply that by 10, and now we see some padding. So A at the top level, and then there's foo, which is an array, where only the element, the second index, is expandable, and that's going to be an object. And now we have this bar, and there we go. There we go. I guess, yeah, that's fine. I guess actually let's do one more thing. If this code is executing, we don't want people to like type, because that might because the code that gets executed is not going to be synchronized with the code that is actually on screen right here. So do that. Where's code? There's actually a read-only property here. Read-only. We're gonna have to pass props. Read-only boolean. Make it optional. I guess we did. Technically, we didn't really have to make that optional, but it's okay. So if the state is if the state is executing, that's read only. Otherwise, it's not. Let's refresh the page and let's put a breakpoint here, and let's try to modify the code. It cannot be modified. All right, awesome. The next thing we need to do is we need to add highlights. So we need to highlight the line of code that the current stack frame is paused at in execution. To enable highlights, actually, I'm going to first disable some plugins that come out of the box with React Code Mirror. To do that, there's this thing called Basic Setup, and because some of the built-in or some of the plugins that come out of the box kind of interferes with our highlighting. So, for example, like this highlight line that you have selected, this highlight gutter line is going to interfere with our highlights. So let's disable that. Highlight active line gutter, and we just set this to false. Highlight active line, and we set that to false. And I think I'm also going to remove the fold gutter. So if I go back here and I click, the line's not highlighted anymore, and neither is the gutter area. So that's good. And to facilitate custom highlights, we're going to actually make another extension plugin. I'll put it in here, highlights.ts, and I'm just gonna copy some code here. This is our extension. We are integrating with CodeMirror, so again, it's customary to like kind of just copy some code. But the way it works is very similar to the breakpoints. Is that instead of this gutter marker now you have like a decoration. And actually, I think I'm going to adjust the color a little bit, like here actually a little bit more gray. But there's also this field, the state field, to like manage all of the highlight marks, and then we have this effect. Once again, there's going to be two types of effects. There's going to be a set effect, and there's going to be a clear effect. We want to run this clear effect when our program is done executing, so that whatever got highlighted during execution doesn't like linger. And then the set, of course, is just to highlight. Maybe this should extend range of having this from and this to. and here's the part that actually like does the highlighting or removes the highlights. Okay, so let's add this to the extension. And let's actually have a look at, so we have to add the highlight field. Have to add the highlight field. And we also need to propagate down the highlight, which is optional. So it's going to be a range. And now we have to listen to the highlight, because we need to actually initiate an effect to actually clear or to set a highlight. So use effect. And this is going to depend on props to highlight. And actually, I think if we are to propagate an effect into a code mirror, we do need to keep a ref of the editor. So let's make a ref. Code mirror ref. Actually, hang on a second. Use ref. Null. Yeah, code mirror ref. Right, here's the types. And ref is editor ref. All right, cool. So now in use effect, we check if there's a highlight, and if there is a highlight, then we want to propagate this set effect. So we do that. The editor has this thing called view, and I have to check if it exists. We have to do the question mark operator, question mark dot operator, and we just dispatch the effect, which how you do it. Highlight effect of, and then you just put your payload in the argument. Of the highlight. Now, if there's no highlight, then we want to dispatch clear. We want to clear the highlight. Sorry, effects. Highlight effect of, and the type is just going to be a clear. So if I just test it with like a random highlight, let's say highlight is equal to I don't know, from like 0 to like 1, let's say. And on the first line, let's add some like random text. Then okay, I guess that doesn't work. It doesn't. No code mirror ref here. Okay, now it works. Move this over this way just to see if our highlight kind of works. I guess our highlight is not quite working. Why is our highlight not working? Okay, so I think what might be happening here is like some sort of like asynchronous instantiation with React Code Mirror. But I'm not entirely sure, and I'm not going to dive too deep into this problem because we're not going to be highlighting like this. We're not going to hard code the highlights. And instead, what's going to happen is that when our code is executing, we're going to track the current stack frame that we're looking at. So this is going to be a number. This is going to point to the current stack frame that we're looking at. And over here, the initial cur is going to be, what is the initial cur going to be? I guess it's going to be the end of the stack. It could also be the beginning, but actually no, it's definitely the end. So it's next.stack dot length, and then over here, so every time we execute a little bit, we're just going to set the current to the end of the call stack. Yeah. So now once we have the current, then we can actually get the lines that need to be highlighted, because remember the diagnostic frame actually gives location. So it gives us the start, the end, which has the one-dimensional index here. Let's go back to app, and so the highlight is just going to be let's put it below code. Highlight. And also we only want to highlight if if we're executing. So the from is going to be stack state state.cur block.start.i. Then the end is going to be this. What happened here? Oh, it's actually 2. It's not end. Let's try this now. Actually, let's reset the default to just a bunch of new lines. And let me set the print here. Let me add some code here. The breakpoint over here, and there we go. It's highlighted. I'm gonna make the color a little bit more obvious. Oh, actually, let's make it red. Make it over here. Let's make it even more red. Maybe maybe here. Maybe like lighter. Yeah. Okay. Why don't we do this? We have to refresh the page. Apply the styles here, and there we go. That's the highlight. Now I'm gonna try some functions. So let's just go back to the Fibonacci example. I always like to use that one. Test programs 0 and 1. F is equal to fib n minus 1. Right, is equal to fib n minus 2, and then return left plus right. Fib 3, put some breakpoints here. And now I'm just going to run this. So there it is, there it is, there it is, there. All right. So what we're missing now is that I should be able to click into one of these frames, and it should be able to show me where the function has paused. But currently, we're only showing the the topmost frame. So this one right here. So let's go ahead and add support for clicking frames. So in stack, we are going to introduce this thing called oncur. Is a number and void, and whenever somebody clicks on a frame, so I guess we can add an on-click handler here. Then it's props.oncur, index I, and I guess we can also highlight it. Do this. So if the current equal to I, then I have to pass down the cur. Current is I, then let's make the border a little bit more vibrant, otherwise it's gray. Down here, let's pass down cur. So if the state is idle, then I guess it could just be -1, otherwise it's state.cur. And on Actually, let's here just to keep things organized. On expand underneath it, underneath expand is going to be on cur, and all this does is cur state if the type executing, then return dot state cur, let's return state. All right, so let's try running this one more time. Put the breakpoints back in and run. If I click this, there we go. We can see like kind of where the stack is or where the code is paused in the stack frame, and in the global frame we're paused here. Let's run. Let's run, and let's go back here. Okay, so we're trying to compute. We're waiting on computing the right side, whereas here we're still waiting on the left. So let's keep running this. Let's check this. Still waiting on the left. Run, and our program is done executing. All right, we are now feature complete. So there's a few things that we can do. Like we could add some more built-in functions, because right now we only have a print. We can't get the length of an array. We can't pop from an array. We can't push onto an array. We can't delete keys either. So all of that like built-in functionality can be added here, and we could also give this app a CSS makeover, because it doesn't look all that appealing right now, because we've just been focused on functionality. So what I'm gonna do for the finishing touches is that I am going to revamp the CSS so it looks a lot better, and then I think I'm just gonna add a couple more built-in functions here. So yeah. All right, this is how the site looks now. So let's breakpoint here, and there's count. And you see the count going up. Clear, remove this breakpoint. Count is now 10, and there we go. So I also added some more built-in functions. So I added some functionality to get the length of an array, to push, to pop, and also to delete keys from an object. But this project is now complete.